Welcome, friend. In the next few hours, you'll explore 100 fascinating facts about space and time, gently organized into 10 chapters. From the structure of the universe to the technologies that carry us beyond Earth, each section is designed to inform, relax, and help you unwind. There's no need to stay fully alert. Let the science guide you to sleep at your own pace. Chapter 1. The structure of the universe. Fact 1. The observable universe stretches across more than 90 billion light-years. The observable universe represents the portion of the entire cosmos that we can see or detect from Earth. Due to the finite speed of light and the age of the universe, currently estimated at approximately 13.8 billion years, we can observe light that has had time to reach us since the cosmic beginning. However, the distance to the edge of the observable universe is not 13.8 billion light-years. It is significantly larger. This discrepancy arises because the universe has been expanding ever since the Big Bang. As light travels toward us, the space it moves through is also stretching. As a result, the most distant galaxies whose light we can detect today are now much farther away than they were when that light first started traveling. Taking this expansion into account, the current diameter of the observable universe is estimated to be over 90 billion light-years. This means that in any direction we look, up, down, left, or right, we can potentially see galaxies that are over 45 billion light-years away. The boundary beyond which we cannot observe is called the cosmic light horizon. Anything beyond that is effectively invisible to us, not because it doesn't exist, but because its light hasn't had time to reach Earth, and possibly never will due to ongoing expansion. This scale not only defines the limits of our observational reach, but also affects calculations involving cosmic volume and density. When cosmologists speak of the observable universe, they often refer to the spherical volume centered around Earth, containing hundreds of billions of galaxies and an estimated 10 through 80 particles. Fact 2. Galaxies cluster together in vast filaments that form a cosmic web. On the largest scales, the distribution of matter in the universe is not uniform. Rather than being scattered randomly, galaxies and galaxy clusters form interconnected structures that span hundreds of millions of light-years. These vast threads of matter are called cosmic filaments, and they are part of a larger architecture often referred to as the cosmic web. This web-like pattern was first hinted at through redshift surveys in the late 20th century, such as the CFA Redshift Survey and later the Sloan Digital Sky Survey, SDSS. These observations revealed that galaxies are not isolated points, but are connected by elongated structures, forming walls, filaments, and clusters with enormous voids in between. Filaments are composed primarily of dark matter, ordinary matter, and hot intergalactic gas. The galaxies that lie within them are thought to have formed at the intersections of these filaments, where matter density was highest during the early stages of the universe. Simulations like the Millennium Simulation and Illustris have confirmed that these filamentary patterns emerge naturally from the gravitational collapse of matter in an expanding universe governed by dark matter and dark energy. These structures act as conduits through which galaxies move, interact, and evolve. The largest known structure in the observable universe, the Hercules Corona Borealis Great Wall, is believed to be a massive assembly of galactic filaments spanning over 10 billion light-years. Though the classification of this structure is debated, it demonstrates the immense scale at which cosmic filaments can occur. Fact 3. Between these filaments lie immense regions of nearly empty space called voids. In contrast to the dense, galaxy-rich filaments of the cosmic web, voids are vast regions of the universe with remarkably low matter density. These regions can span tens to hundreds of millions of light-years and contain very few galaxies, sometimes none at all. Voids are not entirely empty. They still contain dark matter, diffuse gas, and a few isolated galaxies. However, their density is significantly lower than the average matter density of the universe. These underdense regions play an important role in cosmological modeling because they contribute to the large-scale structure and evolution of the universe. The formation of voids is closely tied to the growth of cosmic filaments. As gravitational attraction causes matter to clump into filaments and clusters, the surrounding regions are emptied out, leading to the development of large voids. This process is driven by gravitational instability and is modeled in simulations of structure formation. One of the largest known voids is the Botez void, discovered in 1981. It spans over 300 million light-years and contains very few galaxies relative to its volume. Voids are also important observationally because they allow astronomers to test theories of gravity and dark energy. For example, the motion of galaxies near void boundaries provides insight into how matter responds to gravitational fields in regions of low density. Cosmic voids also offer a relatively quiet environment, free from the gravitational interactions and galactic collisions that are common in denser regions. Studying them gives astronomers a laboratory to test cosmic expansion and to probe the influence of dark energy with minimal interference from local matter concentrations. Fact 4. Dark matter provides the invisible scaffolding that holds galaxies in place. Dark matter is a form of matter that does not emit, reflect, or absorb electromagnetic radiation, making it invisible to conventional telescopes. Despite this, its presence is inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. One of the earliest clues to the existence of dark matter came from the rotation curves of spiral galaxies. Observations in the 1970s showed that stars in the outer regions of galaxies were orbiting faster than expected based on the mass of visible stars and gas. This discrepancy suggested the presence of a large amount of unseen mass exerting gravitational influence. Dark matter is thought to make up about 27% of the total energy content of the universe, while ordinary baryonic matter makes up less than 5%. The remaining content is attributed to dark energy. Though it is not directly observable, dark matter is essential for explaining why galaxies do not fly apart due to their rotational speeds and why they clump together to form larger structures like clusters and filaments. On cosmological scales, dark matter acts as the gravitational framework within which galaxies and galaxy clusters form. It also affects the cosmic microwave background and the distribution of galaxies across the sky. Its properties are being studied using gravitational lensing, cosmic background radiation maps, and simulations of structure formation. Despite decades of research, the exact nature of dark matter remains unknown. Leading candidates include weakly interacting massive particles, when axions, both of which are hypothetical particles that interact very weakly with ordinary matter. Fact 5. Dark energy is a mysterious force pushing the universe to expand faster over time. Dark energy is an unknown form of energy that permeates all of space and accelerates the expansion of the universe. It was first proposed in the late 1990s when two independent teams studying distant Type 1a supernovae discovered that the expansion of the universe was not slowing down as previously thought, but speeding up. This unexpected finding led to the revival of a concept Einstein had once considered, the cosmological constant, as a possible explanation for a repulsive energy component in the universe. Today, dark energy is the leading hypothesis for this phenomenon, and it is estimated to account for roughly 68% of the universe's total energy content. Unlike dark matter, which clusters with galaxies, dark energy appears to be smoothly distributed throughout space. Its effects are not noticeable on small scales, such as within galaxies, but they dominate the dynamics of the universe on large scales. Dark energy's precise nature remains one of the most significant unsolved problems in physics. It may be a constant energy density, cosmological constant, or a dynamic field that evolves over time, as in theories of quintessence. Its behavior is characterized by the equation of state parameter, which relates its pressure to its density. Observations of the cosmic microwave background, baryon acoustic oscillations, and galaxy clustering are used to constrain models of dark energy. Understanding this force is crucial for predicting the ultimate fate of the universe, whether it will expand forever, slow down, or undergo a dramatic transformation. Fact 6. The geometry of the universe appears to be flat on large scales. The overall shape of the universe, its geometry, is determined by the interplay between its energy content and the laws of general relativity. Cosmologists classify the geometry of the universe into three categories: open, closed, and flat. A flat universe follows the rules of Euclidean geometry, where parallel lines remain parallel and the internal angles of a triangle always add up to 180 degrees. Measurements from the cosmic microwave background, CMB, especially those made by missions such as WMAP and Planck, have provided high-precision data on the early universe's structure. These observations suggest that the universe is flat to within a very small margin of error, less than 0.5%. This conclusion is based on the angular size of temperature fluctuations observed in the CMB. If the universe were curved, these fluctuations would appear either larger or smaller than expected due to the warping of space. A flat geometry implies that the total energy density of the universe equals the so-called critical density, the precise amount required to halt expansion in the infinitely distant future. This critical balance is made up of ordinary matter, and dark energy. Most of the contribution, however, comes from dark energy, which accounts for the bulk of the energy required to maintain flatness. The apparent flatness of the universe also supports the theory of cosmic inflation. Inflation proposes that a rapid expansion occurred just moments after the Big Bang, smoothing out any initial curvature and setting the universe on a flat trajectory. This early inflationary phase would stretch space to such an extent that any pre-existing curvature would now be undetectable, making the universe appear flat, even if it started off with slight curvature. Fact 7. The afterglow of the Big Bang still fills the universe as a faint background radiation. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this point, the universe was a hot, opaque plasma where photons scattered off free electrons, making it impossible for light to travel freely. When recombination occurred, photons began to move unimpeded through space. This moment is when the universe became transparent to radiation. The radiation released during this epoch still fills the universe today, though it has been stretched by cosmic expansion into the microwave portion of the electromagnetic spectrum. This relic radiation is known as the cosmic microwave background, CMB, and it is observed as a near-uniform glow across the sky at a temperature of about 2.7 Kelvin. The CMB is not perfectly uniform. It contains slight temperature variations on the order of a few millionths of a degree, which correspond to density fluctuations in the early universe. These fluctuations eventually grew into the large-scale structure we observe today: galaxies, clusters, and filaments. First detected in 1965 by Arno Penzias and Robert Wilson, the CMB has since become one of the most important sources of data in cosmology. High-resolution observations from the COBE, WMAP, and Planck satellites have mapped the CMB in exquisite detail. These maps have allowed scientists to determine the age, composition, and geometry of the universe with remarkable precision. The CMB is also used to test theories of cosmic inflation, dark matter, and dark energy. By examining the angular power spectrum of temperature fluctuations, researchers can extract information about the physics of the early universe and compare it to theoretical predictions. Fact 8. The cosmic web resembles a sponge, with galaxies on the surfaces and emptiness inside. When mapped at very large scales, the universe displays a structure that is both striking and complex. Galaxies are not spread evenly throughout space, but are instead arranged in vast interconnected networks of filaments, walls, and clusters. These features form what is known as the cosmic web, a term that describes the three-dimensional arrangement of matter on the scale of hundreds of millions of light years. The cosmic web is composed primarily of dark matter, which acts as a gravitational framework, drawing ordinary matter into denser regions where galaxies can form. Simulations of cosmic evolution, such as the Millennium and Illustris simulations, show that the cosmic web emerged from initial quantum fluctuations in the early universe that were amplified by gravity over time. This structure resembles a sponge, in the sense that matter tends to gather on the outer boundaries of large voids. The surfaces of these voids are populated by galaxy clusters and filaments, while the interiors remain relatively empty. The result is a three-dimensional mesh where regions of high and low density alternate in a pattern that appears almost cellular. Observational data from surveys like the Sloan Digital Sky Survey (SDSS) confirm this structure. When astronomers map the positions of thousands of galaxies, they find them arranged along thin threads that intersect at nodes, points where multiple filaments converge, forming massive galaxy clusters. These intersections are the densest regions of the cosmic web and often host active galactic nuclei and supermassive black holes. The formation of the cosmic web continues to this day. Galaxies move along the filaments, sometimes merging at the nodes, while gravity slowly drains matter from the surrounding voids. This ongoing motion contributes to the growth of structure and the gradual evolution of the universe. Fact 9. The exact speed of the universe's expansion is still debated by scientists. The expansion of the universe is measured by a parameter known as the Hubble constant. This value describes the rate at which galaxies move away from each other due to the expansion of space itself. The Hubble constant is typically expressed in units of kilometers per second per megaparsec, indicating how much faster a galaxy is receding for every additional million parsecs of distance. Two main methods are used to determine the Hubble constant: the local distance ladder and measurements of the cosmic microwave background. The local distance ladder involves observing nearby Cepheid variable stars and Type 1a supernovae to calculate distances and recession speeds. This method yields a higher value of the Hubble constant. In contrast, the cosmic microwave background method uses data from satellites like Planck to infer the expansion rate by analyzing the conditions of the early universe and extrapolating forward. This technique results in a slightly lower value. The discrepancy between these two measurements is known as the Hubble tension and has become a major puzzle in cosmology. The current difference between the two estimates is statistically significant and has prompted suggestions of new physics beyond the standard model of cosmology. Some theories propose modifications to the behavior of dark energy, while others suggest the existence of previously unknown particles or forces. Resolving the Hubble tension is an ongoing priority in the field. Future telescopes and missions, such as the Nancy Grace Roman Space Telescope and improved ground-based observatories, aim to reduce uncertainties and help clarify whether the tension points to measurement error or deeper physical insights. Fact 10. The total universe could be infinite, even though we can only observe a portion of it. Our ability to study the universe is limited by the speed of light and the finite age of the cosmos. As a result, we can only observe regions from which light has had time to reach us. This defines the observable universe. However, The actual size of the total universe may be vastly greater than what we can see, and it could even be infinite. Current cosmological models based on general relativity allow for an infinite universe that extends endlessly in all directions. If the geometry of the universe is truly flat and has been so since inflation, then there is no requirement for it to have a boundary or edge. Space could continue forever beyond our observable limits. Even if the universe is not infinite, it could still be much larger than the portion we can study. The observable universe is a spherical region centered on Earth, but there are likely other regions beyond our cosmic light horizon that contain galaxies, stars, and matter that we will never be able to observe. The idea of an infinite universe raises interesting implications for both cosmology and physics. It would mean that the same physical laws apply throughout an endless expanse, and that our observable universe is just a small region within a much larger framework. Although we cannot test the infinity of the universe directly, observations of cosmic curvature, the cosmic microwave background, and large-scale structure provide indirect evidence. So far, all available data is consistent with a flat and potentially infinite universe. However, the question remains open, and future observations may provide deeper insight into the true scale of the cosmos. Chapter 2. The Life Cycles of Stars. Fact 1. Stars are born in clouds of gas and dust called nebulae. Star formation begins in vast regions of space known as molecular clouds or stellar nurseries. These clouds are composed primarily of hydrogen gas, along with smaller amounts of helium and trace elements. When portions of these clouds become gravitationally unstable, often due to external forces such as shock waves from nearby supernovae or collisions with other clouds, they begin to collapse under their own gravity. As the material collapses, it fragments into smaller regions known as protostellar cores. These dense cores accumulate mass from their surroundings while gradually heating up due to gravitational compression. At this stage, the object is referred to as a protostar. During this phase, the core remains opaque to its own radiation, and the heating is mainly internal. As the protostar contracts further, the temperature and pressure in the core increase. Eventually, when the core temperature becomes high enough, typically above 10 million degrees Celsius, nuclear fusion reactions begin. Hydrogen atoms start fusing into helium, releasing vast amounts of energy in the process. This marks the transition from a protostar to a main sequence star, a stage in which the outward pressure from fusion balances the inward pull of gravity. Star-forming regions can be observed in various parts of the universe. The Orion Nebula is one of the best studied examples, offering insights into the early stages of stellar birth. Infrared telescopes are particularly useful for observing star formation, as the dense dust in these regions often obscures visible light. Fact 2. The Sun is roughly halfway through its life as a stable star. The Sun is classified as a G-type main sequence star, also known as a G-dwarf. It has been steadily fusing hydrogen into helium in its core for about 4.6 billion years, and is expected to remain in this stable phase for approximately another 5 billion years. This makes the Sun roughly halfway through its main sequence lifetime. Main sequence stars generate energy through hydrogen fusion in their cores via the proton-proton chain reaction. This process releases energy in the form of gamma rays, which gradually travel through the Sun's radiative and convective zones before reaching the surface and escaping as visible light and other forms of electromagnetic radiation. The balance between gravitational contraction and the outward pressure from fusion reactions keeps the Sun stable during this phase. Over time, as hydrogen in the core is converted into helium, the core contracts slightly and heats up. This causes the outer layers of the Sun to expand and its luminosity to increase gradually. Eventually, when the hydrogen in the Sun's core is depleted, it will leave the main sequence and enter the red giant phase. During that period, fusion will occur in shells around a growing helium core, leading to changes in the sun's structure and energy output. But for now, the sun remains a relatively quiet and stable star, providing a consistent source of energy for the solar system. Fact 3. The mass of a star determines how it lives and how it dies. A star's mass is the most important factor in determining its life cycle. Stellar mass governs the core temperature, pressure, luminosity, and the types of nuclear reactions that occur during the star's lifetime. It also dictates the star's lifespan and its eventual fate. Low-mass stars, those with less than about 0.5 times the mass of the sun, burn their hydrogen fuel very slowly. These stars, known as red dwarfs, can have lifespans extending up to trillions of years. Due to their long lifetimes and efficient fusion processes, no red dwarfs have yet reached the end of their life in the observable universe. Stars with masses similar to the sun's follow a well-understood evolutionary path. They spend billions of years on the main sequence, then expand into red giants as hydrogen runs out in the core. Eventually, they shed their outer layers to form planetary nebulae and leave behind white dwarfs, dense stellar remnants composed mostly of carbon and oxygen. More massive stars, typically those exceeding about 8 solar masses, evolve more rapidly due to their higher core temperatures and fusion rates. These stars progress through a series of fusion stages, forming heavier elements like carbon, oxygen, neon, and iron. Once an iron core develops, fusion can no longer generate net energy, leading to a catastrophic core collapse. This results in a supernova explosion, leaving behind either a neutron star or a black hole. The star's mass also affects its spectral type, color, and luminosity. More massive stars are hotter and bluer, while less massive stars are cooler and redder. Mass is thus the key variable that defines the entire evolutionary track of a star from birth to final state. Fact 4. Massive stars burn hotter and die younger than smaller stars. Stars with high masses, typically more than 8 times the mass of the sun, have much shorter lifespans than their lower mass counterparts. This is because they consume their nuclear fuel at significantly higher rates. Despite having more hydrogen available, the increased core temperature in massive stars accelerates the fusion process, leading to lifespans of only a few million years in some cases. Massive stars begin their lives on the main sequence with intense brightness and high surface temperatures. They often belong to the spectral classes O and B, characterized by blue or bluish-white coloration. The immense radiation pressure from their luminous output drives strong stellar winds, which can lead to substantial mass loss over time. As fusion progresses, massive stars evolve through a series of increasingly advanced nuclear reactions. They burn hydrogen to helium, helium to carbon, and so on, eventually producing heavier elements like silicon and iron. Each fusion stage lasts progressively shorter periods. For example, hydrogen fusion might last millions of years, while iron fusion, if it occurs, lasts only a few seconds. The endpoint comes when the star develops an iron core. Since iron fusion consumes energy instead of releasing it, the core becomes unstable and collapses under gravity. This rapid implosion causes the outer layers to rebound in a violent supernova explosion. Because of their short lives and powerful outputs, massive stars play a key role in enriching the interstellar medium with heavy elements. They also influence the dynamics of their surroundings through radiation, winds, and eventual supernova remnants. Fact 5. Red giants swell to enormous sizes before shedding their outer layers. As a star like the sun exhausts hydrogen in its core, it can no longer maintain the same level of outward pressure from fusion. The core contracts under gravity and heats up, igniting hydrogen in a shell surrounding the core. This new energy source causes the star's outer layers to expand dramatically, marking the beginning of the red giant phase. During the red giant stage, the star becomes significantly larger in radius and more luminous, although its surface temperature drops. giving it a reddish hue. The Sun, for example, is expected to expand to a radius that may engulf the orbits of Mercury and Venus during its red giant phase. As the core continues to contract and heat up, helium fusion begins in the core in a process known as the helium flash for stars around the Sun's mass. This leads to the fusion of helium into carbon and oxygen. Over time, the star becomes unstable again as helium is depleted, and multiple fusion shells develop around the inert core. The outer layers of the red giant become increasingly unstable and are eventually ejected into space through strong stellar winds and thermal pulsations. The material released during this phase forms a planetary nebula, a glowing shell of gas illuminated by the remaining stellar core. What remains after the red giant sheds its outer layers is a dense, Earth-sized core known as a white dwarf. This object no longer undergoes fusion, but continues to cool over billions of years. The planetary nebula will fade, but the white dwarf remains as a silent remnant of the once active star. Fact 6. White dwarfs are the fading remnants of small stars like our Sun. When a star with an initial mass up to approximately 8 times that of the Sun exhausts its nuclear fuel, it enters the final stages of its evolution. After progressing through the red giant phase and shedding its outer layers, the star leaves behind a compact core. This remnant is known as a white dwarf, a dense, Earth-sized object composed primarily of carbon and oxygen. White dwarfs no longer undergo fusion reactions. Instead, they shine due to residual thermal energy, gradually cooling and fading over billions of years. These objects are supported against further collapse by a quantum mechanical phenomenon called electron degeneracy pressure. According to the Pauli exclusion principle, electrons cannot occupy the same quantum state, and this resistance provides a stabilizing force that counteracts gravity. The typical mass of a white dwarf is about 0.6 times that of the Sun, while its volume is comparable to that of Earth. This results in a density so high that a cubic centimeter of white dwarf material can weigh several tons. Despite their small size, white dwarfs retain most of the mass of their progenitor stars. White dwarfs occupy the lower left portion of the Hertzsprung-Russell diagram and follow a predictable cooling sequence. Over time, they emit less and less light and eventually become what is theoretically called a black dwarf, a cold, dark stellar corpse. However, given the current age of the universe, no black dwarfs are believed to exist yet. Some white dwarfs exist in binary systems where they may accrete matter from a companion star. If enough mass accumulates to push the white dwarf over the Chandrasekhar limit, approximately 1.4 times the mass of the Sun, it can trigger a thermonuclear explosion, resulting in a type Ia supernova. Fact 7. Neutron stars are incredibly dense and form after supernova explosions. Neutron stars are one of the possible end states of massive stars. When a star with an initial mass greater than about 8 solar masses exhausts its nuclear fuel, it can no longer resist gravitational collapse. If the remaining core is between roughly 1.4 and 3 solar masses after a supernova, it becomes a neutron star. A neutron star is composed almost entirely of neutrons, created when electrons and protons are crushed together under extreme pressure during core collapse. The resulting object has an incredibly small radius, typically about 10 to 12 kilometers, yet it contains more mass than the Sun. The density of a neutron star is so extreme that a single teaspoon of its material would weigh billions of tons. Neutron stars are stabilized by neutron degeneracy pressure, another quantum mechanical effect similar to electron degeneracy in white dwarfs but involving neutrons. This force prevents further collapse unless the mass exceeds a certain threshold, in which case the object may become a black hole. Neutron stars exhibit remarkable physical properties. They possess extremely strong magnetic fields, often trillions of times stronger than Earth's. They also rotate very rapidly, some spin hundreds of times per second. These rapidly rotating neutron stars are known as pulsars, which emit beams of electromagnetic radiation that sweep across the sky like a lighthouse. The study of neutron stars provides insights into nuclear physics, relativity, and the behavior of matter under extreme conditions. Observations are typically conducted using radio, X-ray, and gamma-ray telescopes, which can detect the pulsations and bursts associated with these exotic objects. Fact 8. Supernovae spread heavy elements throughout the galaxy. A supernova is the explosive death of a star, resulting in the rapid ejection of stellar material into space. There are several types of supernovae, but all involve the release of an enormous amount of energy in a short period of time. These explosions play a crucial role in galactic ecology by dispersing the elements created within stars into the surrounding interstellar medium. Massive stars end their lives as core collapse supernovae. When the core of a massive star collapses under gravity, it forms a neutron star or black hole, and the outer layers are blasted into space. During the explosion, temperatures and pressures are so extreme that new elements are synthesized in a process known as explosive nucleosynthesis. This creates elements heavier than iron, such as gold, uranium, and platinum. Type 1a supernovae occur in binary systems, where a white dwarf accumulates mass from a companion star until it reaches a critical limit. This leads to a runaway fusion reaction that destroys the white dwarf. Type 1a supernovae are especially important in astronomy because they have consistent luminosities, making them valuable as standard candles for measuring cosmic distances. The remnants of supernova, known as supernova remnants, are composed of expanding shells of gas and dust. These remnants interact with surrounding material, triggering shock waves that can compress nearby gas clouds and initiate new waves of star formation. Thus, supernovae not only recycle matter, but also contribute to the birth of new stars and planetary systems. The evidence of past supernovae can be seen in features like the Crab Nebula, which is the remnant of a supernova observed in 1054 CE. Supernovae have also been detected in other galaxies and are an essential observational target in modern astrophysics. Fact 9. Stars create elements like carbon and oxygen in their cores. The process of nuclear fusion is central to stellar life. Inside the cores of stars, lighter elements are fused into heavier ones under immense pressure and temperature. The fusion of hydrogen into helium is the primary energy source for most stars during the main sequence phase. However, as stars evolve, they begin to fuse heavier elements in successive stages. Once hydrogen is exhausted in the core, the star contracts and heats up, enabling helium fusion. This process produces elements like carbon and oxygen. In stars with sufficient mass, further contraction and heating allow for the fusion of carbon into neon, oxygen into silicon, and so forth, forming progressively heavier elements up to iron. The formation of elements through fusion is referred to as stellar nucleosynthesis. This process not only powers the star, but also produces the elemental building blocks of planets, atmospheres, and eventually life. The specific pathways depend on the mass and temperature of the star. For example, low-mass stars may only reach the helium burning phase, while high-mass stars can proceed through multiple stages all the way to iron. Iron represents a special case in stellar evolution. Fusion of iron does not release energy, it requires it. As a result, once a massive star accumulates an iron core, it can no longer sustain fusion to counteract gravity. This leads to core collapse and a supernova explosion. The elements formed in stellar cores are released into space during the final stages of a star's life, enriching the interstellar medium. This material is then incorporated into new generations of stars, creating a continuous cycle of element formation and redistribution. Fact 10. The universe's first stars may have been hundreds of times more massive than the Sun. The earliest stars in the universe, known as population 3 stars, are believed to have formed from primordial gas composed almost entirely of hydrogen and helium. These stars formed in the first few 100 million years after the Big Bang, before the universe was enriched with heavier elements. Due to the absence of metals, defined in astronomy as elements heavier than helium, cooling processes in the gas clouds were less efficient. This limited fragmentation during gravitational collapse, leading to the formation of more massive stars. Simulation suggests that some of these stars could have reached masses exceeding 100 times that of the Sun, with some possibly as massive as 300 solar masses. These extremely massive stars had very short lifespans, often only a few million years. They burned through their fuel rapidly and likely ended their lives in hypernovae or pair instability supernovae, depending on their mass. These explosions would have been capable of producing large amounts of heavy elements and dispersing them widely, contributing to the chemical enrichment of the early universe. Despite their theoretical importance, population 3 stars have not yet been directly observed. However, their existence is inferred from the chemical composition of extremely metal-poor stars found in the halo of our galaxy. These ancient stars likely formed from gas enriched by the first generation of supernovae. Future telescopes, such as the James Webb Space Telescope and upcoming ground-based observatories, may provide indirect evidence or even detect light from population 3 stars in distant galaxies. Understanding these stars is essential for piecing together the early stages of cosmic evolution, including the formation of the first galaxies and the reionization of the universe. Chapter 3: Planetary Systems and Exoplanets. Fact 1. Thousands of planets have been discovered orbiting stars beyond our solar system. Since the early 1990s, the discovery of planets orbiting stars outside our solar system, called exoplanets, has revolutionized our understanding of planetary systems. As of 2025, more than 5,000 confirmed exoplanets have been cataloged, with thousands more awaiting confirmation. These discoveries have been made possible by advancements in observational technology and data analysis techniques. The first confirmed detection of an exoplanet around a Sun-like star was 51 Pegasi b, discovered in 1995 using the radial velocity method. However, even earlier detections had been made around pulsars. Since then, several space-based missions, most notably NASA's Kepler Space Telescope and its successor TESS, Transiting Exoplanet Survey Satellite, have been instrumental in identifying exoplanets in various star systems. The range of planetary types discovered has vastly expanded our understanding of how planets form and evolve. Exoplanets have been found in a wide variety of sizes, orbital configurations, and compositions. Some resemble Earth, while others are gas giants larger than Jupiter. The discovery of these planets has shown that planetary systems are common in the galaxy, and that our own solar system is only one example among many. Exoplanets have been found in binary star systems, around red dwarfs, and in wide orbits far from their host stars. These findings challenge previous models that assumed planetary systems would resemble our own. The growing catalog of exoplanets continues to inform models of planetary formation, migration, and atmospheric composition. Fact 2. Some giant planets orbit their stars so closely that their atmospheres are scorched. A particularly surprising category of exoplanets discovered is the class known as hot Jupiters. These are gas giant planets similar in mass and size to Jupiter, but with orbits that bring them extremely close to their parent stars, often much closer than Mercury is to the Sun. As a result, these planets experience intense irradiation and extreme atmospheric conditions. Hot Jupiters typically have orbital periods ranging from a few days to less than a week. Due to their proximity to their host stars, they are often tidally locked, meaning the same side always faces the star. This leads to a permanent day side with very high temperatures and a night side that is relatively cooler. Temperatures on the irradiated side can exceed 1,500 degrees Celsius and in some cases even reach over 2,000 degrees. The intense heat causes significant atmospheric expansion and in some cases, atmospheric escape. Observations using space telescopes such as Hubble and Spitzer have revealed extended, escaping atmospheres trailing behind some hot Jupiters, indicating that stellar radiation can strip lighter elements from their outer layers. In extreme cases, this may lead to significant mass loss over time. Hot Jupiters also exhibit strong atmospheric winds, with speeds potentially reaching several kilometers per second. Infrared measurements have shown that heat can be redistributed across the planet through these high-velocity winds, although the efficiency of this process varies among different planets. Their existence posed an initial challenge to traditional models of planetary formation, which predicted that gas giants should form far from their host stars, beyond the so-called frost line. The discovery of hot Jupiters led to the development of new theories, including orbital migration, where planets form at greater distances and move inward over time due to interactions with the protoplanetary disk or other planets. Fact 3. Free-floating planets exist between stars, drifting through space alone. In addition to planets that orbit stars, astronomers have discovered a class of objects known as free-floating planets or rogue planets. These planetary mass objects do not orbit any star and instead travel through interstellar space on their own. Their detection is challenging as they emit little or no light and are not gravitationally bound to a stellar system. Rogue planets are thought to form in two main ways. First, they may form in protoplanetary disks like regular planets, but later be ejected from their systems due to gravitational interactions with other planets or passing stars. Second, they may form in isolation through direct collapse in molecular clouds, similar to how brown dwarfs form, but with masses below the threshold for hydrogen fusion. Because they do not reflect or emit significant visible light, rogue planets are typically detected using indirect methods. One of the most effective techniques is gravitational microlensing, where a rogue planet passes in front of a more distant star and briefly magnifies its light due to gravitational lensing. This allows astronomers to estimate the planet's mass and motion. Surveys using this method have suggested that there may be as many rogue planets as there are stars in the galaxy, perhaps even more. These objects represent a significant but largely unexplored population of planetary bodies that could provide new insights into planet formation and the dynamics of planetary systems. Some theories speculate that rogue planets may retain internal heat for long periods, allowing them to have subsurface oceans or thick atmospheres. However, their isolation makes them much harder to study in detail than planets orbiting luminous stars. Fact 4. Planets are often found by watching for tiny dips in a star's brightness. One of the most successful techniques for detecting exoplanets is the transit method. This technique involves observing a star's light output over time and looking for periodic dimming that occurs when a planet passes or transits in front of the star from our line of sight. The dip in brightness is typically very small, often less than 1%, but can be detected with highly sensitive instruments. The Kepler Space Telescope was specifically designed to use this method and monitored over 150,000 stars simultaneously. It identified thousands of planet candidates by detecting these characteristic light curves. TESS continues this work, focusing on nearby bright stars to facilitate follow-up observations. When a planet transits its host star, it not only reveals the presence of the planet, but also provides valuable information about its size, orbital period, and in some cases, atmospheric properties. The depth of the transit reveals the planet's size relative to the star, while the duration and timing yield its orbital characteristics. In multi-planet systems, variations in the timing of transits can also be used to infer the presence of additional non-transiting planets through gravitational interactions, a method known as transit timing variations. One of the limitations of the transit method is that it requires near-perfect alignment between the planet's orbit and our line of sight, meaning that only a small percentage of planetary systems are detectable this way. Nonetheless, its high efficiency and ability to provide detailed data have made it a cornerstone of modern exoplanetary science. Fact 5. Another method detects them by measuring how their gravity tugs on their star. The radial velocity method is another cornerstone of exoplanet detection. It involves measuring the tiny shifts in a star's spectral lines caused by the gravitational pull of an orbiting planet. As the planet orbits, it causes the star to move in a small, reflexive orbit. This motion creates a Doppler shift in the star's light. It moves slightly toward and then away from Earth, alternately compressing and stretching the wavelengths of light we observe. Using high-resolution spectrographs, astronomers can detect these shifts and infer the presence of a planet. The amplitude and periodicity of the velocity variations allow researchers to determine the planet's minimum mass and orbital parameters. The radial velocity method was responsible for the first confirmed detection of an exoplanet around a Sun-like star, 51 Pegasi b. It remains a vital technique, particularly for studying planetary systems around bright, far nearby stars. It is also complementary to the transit method. When both methods are applied to the same system, they can provide a planet's true mass and density, revealing whether it is gaseous, rocky, or somewhere in between. One of the limitations of this method is that it is most sensitive to massive planets close to their stars, which produce larger radial velocity signals. Detecting Earth-sized planets requires extremely precise measurements, often at the level of meters or even centimeters per second, which is at the limit of current technology. However, new instruments, such as the espresso spectrograph, are pushing these boundaries. The radial velocity technique has been instrumental in the development of planetary formation models, especially in identifying gas giants in close orbits, which were once thought to be rare. It continues to contribute to the discovery and characterization of a wide range of exoplanets. Fact 6. Some planets have orbits that are highly stretched out or tilted. Planetary orbits can exhibit a wide range of shapes and orientations. While the planets in our solar system have relatively circular and aligned orbits, many exoplanets have orbits that are highly eccentric, meaning they are stretched into elongated ellipses rather than nearly perfect circles. Others have significant orbital inclinations, meaning their orbital planes are tilted relative to the equatorial plane of their host star. Eccentric orbits result in dramatic changes in distance between the planet and its star during a single orbit. At closest approach periastron, the planet may receive intense stellar radiation, while at the farthest point, apastron, it could experience much cooler conditions. These orbital configurations lead to significant variations in surface temperature and atmospheric dynamics, assuming the planet has an atmosphere. Tilted or misaligned orbits, including retrograde orbits where the planet moves in the opposite direction of the star's rotation, are also of great interest. These misalignments are detected using the Rossiter-McLaughlin effect, which analyzes changes in a star's spectral line profile during a planetary transit. Studies have shown that many hot Jupiters exhibit orbital inclinations significantly different from their star's equator, suggesting that interactions after formation may have altered their paths. These orbital anomalies often result from gravitational perturbations such as planet-planet interactions, Kozai-Ladov oscillations from a distant companion, or scattering events in the early stages of the system's evolution. Such findings challenge traditional models of planet formation, which predict that planets should form in aligned, circular orbits within a protoplanetary disk. The prevalence of eccentric and tilted orbits among exoplanets has led to the development of refined models of planetary migration and dynamical instability. These models now account for the long-term gravitational interactions that can significantly alter orbital elements after the initial formation process. Fact 7. Rocky worlds larger than Earth are known as super-Earths. Super-Earths are a class of exoplanets that have masses greater than Earth's, but significantly less than those of ice giants like Neptune and Uranus. Typically, they are defined as having masses between about 1.2 and 10 Earth masses. Despite the name, super-Earth refers only to size and mass, not to habitability or surface conditions. These planets exhibit a range of compositions, from dense, rocky bodies to planets with significant atmospheres and volatile content. Determining a super-Earth's composition requires both its radius, usually derived from the transit method, and its mass, commonly obtained via the radial velocity method. The resulting density allows scientists to estimate whether the planet is predominantly rocky, water-rich, or enveloped in gas. Super-Earths have proven to be one of the most common types of exoplanets found to date, especially around M-dwarf stars. Some of these planets lie within their star's habitable zone, prompting detailed investigations into their potential atmospheric properties and surface conditions. A well-known example is the planet LHS 1140b, a dense, rocky super-Earth orbiting within the habitable zone of a nearby red dwarf. Another is Kepler 452b, which orbits a Sun-like star and is about 60% larger in diameter than Earth. These planets provide key observational targets for upcoming atmospheric characterization missions. The diversity of super-Earths reveals the complexity of planetary formation and evolution. Some may have plate tectonics, molten mantles, or thick atmospheres of hydrogen and helium. Others may lack magnetic fields or be locked in synchronous rotation. The wide variation among these planets provides a valuable laboratory for comparative planetology. Fact 8. A planet's distance from its star determines whether it could host liquid water. The concept of a star's habitable zone, the region where conditions might allow for liquid water on a planet's surface, is central to the search for potentially life-supporting exoplanets. This region depends primarily on the star's luminosity and the planet's distance from it. Planets too close to their star receive excessive energy and are likely to experience a runaway greenhouse effect, while those too far receive too little energy to maintain liquid water. The inner and outer boundaries of the habitable zone are calculated using models that account for the planet's atmospheric composition and reflectivity. For a Sun-like star, the classical habitable zone ranges roughly from 0.95 to 1.37 astronomical units AU. For smaller stars, the zone lies much closer in. For more massive stars, it shifts outward. A planet's surface temperature is also influenced by greenhouse gases in its atmosphere. For instance, a dense carbon dioxide atmosphere can trap heat and allow for warmer temperatures farther from the star. Conversely, a planet with a thin or absent atmosphere might not retain enough heat, even if located within the formal habitable zone. Factors such as orbital eccentricity and axial tilt can cause additional variations in climate and thermal distribution. Planets on highly elliptical orbits may spend only part of their orbit in the habitable zone, raising questions about the stability of liquid water under such conditions. Not all potentially habitable planets lie neatly within the classic habitable zone. Moons of giant planets, planets with subsurface oceans, or planets with exotic atmospheric compositions may support stable liquid water under different conditions. As such, the habitable zone is a useful guideline but not a definitive predictor of surface conditions. Fact 9. Planet formation begins in disks of dust and gas around young stars. Planets form in protoplanetary disks, flattened, rotating structures of gas and dust that encircle young stars. These disks are the byproduct of the star formation process, which involves the collapse of a molecular cloud. As material falls inward to form the star, conservation of angular momentum causes the surrounding material to flatten into a disk. The initial stages of planet formation involve the coagulation of dust grains within the disk. These grains collide and stick together, forming larger aggregates called planetesimals. Once planetesimals reach sizes of several kilometers, their gravitational influence becomes significant, allowing them to attract more material and grow into planetary embryos. In the core accretion model, these embryos can accumulate enough mass to become full-fledged terrestrial planets or serve as cores for gas giants. If the protoplanetary disk still contains enough gas and the core reaches a critical mass before the disk dissipates, it can accrete a thick atmosphere of hydrogen and helium, forming a gas giant. Otherwise, the planet remains rocky or icy. Disk lifetimes are typically short in astronomical terms, lasting only a few million years. During this time, radiation from the central star and other nearby stars can drive photoevaporation of the disk, halting gas accretion and influencing planetary composition. Disk observations using facilities like ALMA, Atacama Large Millimeter Submillimeter Array, have revealed gaps, rings, and asymmetries that likely indicate ongoing planet formation. These structures provide direct evidence of young planets interacting gravitationally with their birth environment. Planet migration, a process where forming planets interact with the gas disk and spiral inward or outward, is also thought to play a key role in shaping planetary system architectures. Migration can explain the presence of hot Jupiters and compact multi-planet systems observed by Kepler. Fact 10. Some alien worlds may have endless oceans or thick, hazy skies. The diversity of exoplanetary atmospheres and surface conditions has led scientists to consider the possibility of planets that do not resemble anything found in our solar system. Among these are ocean worlds, planets that may be entirely covered by deep global oceans, and those with thick, cloud-laden atmospheres rich in exotic compounds. Ocean worlds are expected to form in regions rich in water ice or to accrete significant volatiles from their natal disks. These planets may lack any exposed landmass and could have oceans hundreds of kilometers deep, potentially overlying a layer of high-pressure ice. Without tectonic activity or land to regulate carbon cycles, their climate dynamics could be substantially different from Earth's. Examples of potential ocean worlds include planets like GJ1214b and K218b. Observations of K218b suggest the presence of water vapor in its atmosphere and a mass that is consistent with a water-rich composition. However, the planet's thick atmosphere may create surface pressures and temperatures far beyond Earth-like levels. Other exoplanets may be shrouded in thick, hazy atmospheres dominated by compounds such as methane, ammonia, or hydrogen sulfide. These atmospheres can obscure direct observations and may be the result of outgassing, photochemical reactions, or primordial gas accretion. Observations using transmission spectroscopy during planetary transits allow scientists to analyze starlight that filters through these atmospheres, revealing chemical fingerprints. Atmospheric modeling helps determine whether these planets experience greenhouse effects, atmospheric escape, or cloud formation. Theoretical studies and data from missions like JWST are expected to expand our understanding of such worlds and clarify the boundaries between rocky super-Earths, mini-Neptunes, and volatile-rich planets. Chapter 4. Black Holes and Neutron Stars. Fact 1. A black hole's boundary is called the event horizon. Nothing escapes once it's crossed. A black hole is defined by a boundary in spacetime known as the event horizon. This is the region beyond which nothing, not even light, can escape the gravitational pull of the black hole. The event horizon is not a physical surface, but a mathematical boundary. Once an object crosses it, all paths lead inward toward the singularity. The event horizon forms when a massive object collapses under its own gravity. For a non-rotating, uncharged black hole, the size of this boundary is described by the Schwarzschild radius. The radius depends directly on the mass of the black hole. The more massive the black hole, the larger the event horizon. The concept of an event horizon comes directly from the equations of general relativity, which describe how mass and energy warp space-time. At the event horizon, the escape velocity equals the speed of light. That means any object, regardless of its energy, would require more than the speed of light to escape, which is not permitted under the current laws of physics. Although the interior of a black hole remains hidden, the event horizon acts as an observable boundary that can be indirectly studied. For example, light emitted from material near the horizon appears increasingly redshifted and dimmer as it approaches the boundary due to gravitational redshift. The Event Horizon Telescope (EHT) collaboration captured the first image of a black hole's shadow in the galaxy M87. What was observed was the region just outside the event horizon, where hot plasma emitted detectable radiation. While the event horizon itself cannot be imaged, the gravitational influence it exerts is apparent in the behavior of nearby matter. Fact 2. The size of a black hole's horizon depends on its mass. The radius of the event horizon, often referred to as the Schwarzschild radius in the case of a static, non-rotating black hole, is directly proportional to the mass of the black hole. This relationship is one of the simplest features of black holes derived from general relativity. Mathematically, the Schwarzschild radius increases linearly with mass. This means that doubling the mass of a black hole doubles the radius of its event horizon. In physical terms, the radius is the distance from the center of the black hole to the point where the escape velocity equals the speed of light. Stellar mass black holes, which result from the collapse of massive stars, typically have Schwarzschild radii of a few kilometers. In contrast, supermassive black holes, which reside at the centers of galaxies, can have event horizons spanning millions of kilometers. For example, the supermassive black hole in the center of the Milky Way, known as Sagittarius A, has a mass of about 4 million times that of the Sun, corresponding to an event horizon roughly the size of the orbit of Mercury. The linear relationship between mass and horizon size plays a crucial role in black hole thermodynamics, gravitational wave physics, and accretion disk dynamics. It affects how black holes interact with their environments and how they can be detected through indirect means such as gravitational lensing or X-ray emissions. In the case of rotating, Kerr, or charged Reissner-Nordstrom black holes, the situation is more complex. These black holes possess an outer event horizon and an inner horizon due to additional terms in the metric equations, and the shape of the event horizon becomes oblate. However, the dependency on mass remains a foundational characteristic. Fact 3. When a very massive star collapses, it can become a black hole. Black holes can form as an end result of stellar evolution in massive stars. During a star's lifetime, nuclear fusion generates outward pressure that balances the inward pull of gravity. As the star exhausts its nuclear fuel, this balance is lost and the core collapses. In stars with initial masses greater than approximately 20 to 25 times that of the Sun, the core collapse can be so intense that no known force can halt it. After the core reaches a critical density, electrons and protons combine into neutrons. If the core mass exceeds the maximum supportable limit for a neutron star, known as the Tolman-Oppenheimer-Volkoff limit, estimated to be around 2 to 3 solar masses, it continues collapsing into a singularity, forming a black hole. The outer layers of the star may be ejected in a supernova explosion, while the core collapses inward. Depending on the mass and energy conditions, the black hole may form directly or through fallback, where expelled material falls back onto the remnant and pushes it past the critical mass. Black holes formed through stellar collapse are known as stellar mass black holes. and are typically found in the range of 3 to 100 solar masses. Observations of X-ray binaries, gravitational waves, and supernova remnants provide indirect evidence for their existence. The detection of gravitational waves from binary black hole mergers by the LIGO and Virgo observatories has provided strong confirmation of this formation channel. The masses and spins of the merging black holes give insight into the properties of their progenitor stars and the environments in which they formed. Fact 4. Gigantic black holes live at the centers of most large galaxies. Supermassive black holes, with masses ranging from millions to billions of times that of the Sun, are believed to reside at the centers of most large galaxies. These objects are fundamentally different from stellar mass black holes in scale and likely in formation mechanism. Evidence for the existence of supermassive black holes comes from multiple observations. The motions of stars and gas near galactic centers indicate the presence of a compact, massive object exerting a strong gravitational pull. In the case of the Milky Way, observations of stellar orbits near the center have revealed a mass of about 4 million solar masses confined to a very small region, consistent with a supermassive black hole. Active galactic nuclei, AGN, quasars, and radio galaxies are powered by accretion onto supermassive black holes. As matter spirals into the black hole, it forms an accretion disk and heats up due to friction and compression, emitting vast amounts of energy across the electromagnetic spectrum. The mechanism by which these black holes grow remains an area of active research. Theories include direct collapse of massive gas clouds in the early universe, growth through mergers with other black holes, and accretion of gas over billions of years. Observations of quasars at high redshifts suggest that some supermassive black holes formed less than 1 billion years after the Big Bang, indicating very rapid growth. The presence of supermassive black holes appears to be correlated with properties of their host galaxies, such as bulge mass and velocity dispersion. This suggests a coevolutionary relationship between galaxies and their central black holes, possibly mediated through feedback processes involving jets and radiation. Fact 5. Neutron stars are so dense that a single teaspoon of their material would weigh billions of tons. Neutron stars are the remnants of massive stars that have undergone supernova explosions, but whose cores were not massive enough to form black holes. These stellar remnants are composed almost entirely of neutrons and are among the densest forms of matter in the universe. A typical neutron star has a mass between 1.1 and 2.3 times that of the Sun, but is only about 10 to 12 kilometers in radius. This results in an average density exceeding that of an atomic nucleus. To put this into perspective, a single cubic centimeter of neutron star material could weigh hundreds of millions of tons on Earth. A teaspoon of such material, roughly 5 cubic centimeters, would weigh billions of tons. The structure of a neutron star includes a solid crust made of neutron-rich nuclei and electrons, a superfluid interior of neutrons, and possibly exotic phases of matter in the core. The equation of state of neutron star matter, describing how pressure relates to density, is still not fully known and is a key focus of current research. Neutron stars are supported against gravitational collapse by neutron degeneracy pressure, a quantum mechanical force arising from the Pauli exclusion principle. This pressure is similar in nature to the electron degeneracy pressure that supports white dwarfs but involves neutrons instead of electrons. Observations of neutron stars are conducted across multiple wavelengths. Pulsars, a type of rapidly rotating neutron star, emit beams of radio waves detectable on Earth. Other neutron stars are observed in X-rays, particularly when accreting matter from a companion star. Recent gravitational wave detections from neutron star mergers have provided new information about their internal structure, the synthesis of heavy elements during collisions, and constraints on the equation of state of dense nuclear matter. Fact 6. Some neutron stars spin rapidly and send out beams of radiation. Neutron stars that rotate rapidly and emit beams of electromagnetic radiation are known as pulsars. These beams are typically observed in the radio frequency range, but can also occur in visible, X-ray, and gamma-ray bands, depending on the characteristics of the pulsar. The emission is caused by highly energetic particles being accelerated along magnetic field lines near the star's magnetic poles. As the neutron star rotates, the beams sweep through space like a lighthouse. If Earth lies in the path of these sweeping beams, the pulsar appears to pulse on and off at regular intervals. This periodicity is extremely stable, with some pulsars maintaining rotational precision comparable to atomic clocks. For example, millisecond pulsars can rotate hundreds of times per second, and their timing is predictable to better than 1 part in a trillion. Pulsars are typically classified into several categories. Young pulsars are usually associated with supernova remnants and have strong magnetic fields and longer periods. Millisecond pulsars, on the other hand, are older neutron stars that have been spun up through the accretion of matter from a companion star in a binary system. This process transfers angular momentum, increasing the neutron star's rotation rate dramatically. The mechanism by which pulsars emit radiation is still an area of active research. Current models suggest that as the star's magnetic field rotates, it induces electric fields that accelerate charged particles. These particles follow curved paths along magnetic field lines and emit curvature radiation, which is highly directional and polarized. Pulsars are invaluable astrophysical tools. They serve as precise cosmic clocks for studying gravitational waves, probing interstellar medium properties, and testing general relativity. Observations of binary pulsars, for instance, have provided direct evidence for gravitational wave emission through orbital decay consistent with predictions of Einstein's theory. Fact 7. Over time, black holes may slowly shrink by releasing faint particles. The idea that black holes can slowly lose mass over time through a quantum mechanical process is known as Hawking radiation. This phenomenon, proposed by Stephen Hawking in 1974, arises from the interaction of quantum fields near the event horizon of a black hole. According to quantum field theory, the vacuum of space is not truly empty, but is filled with transient particle-antiparticle pairs that continuously form and annihilate. Near the event horizon, these pairs can be separated by the intense gravitational field. One particle may fall into the black hole while the other escapes, appearing as radiation emitted from just outside the event horizon. The escaping particle carries energy away from the black hole, effectively reducing its mass. This process is incredibly slow for large black holes. For a stellar mass black hole, the Hawking radiation temperature is many orders of magnitude below the cosmic microwave background, making it virtually undetectable with current instruments. However, for hypothetical primordial black holes with much smaller masses, Hawking radiation could be significant and even lead to complete evaporation over cosmological timescales. The loss of mass through Hawking radiation implies that black holes are not entirely black and can eventually disappear, leaving behind no trace except their emitted radiation. This raises fundamental questions about the conservation of information, a topic known as the black hole information paradox. Despite the lack of direct observational evidence for Hawking radiation, its theoretical foundation is widely accepted. It bridges general relativity, quantum mechanics, and thermodynamics, contributing to the field of quantum gravity and stimulating the development of new theories, including string theory and holographic duality. Fact 8. Near a black hole, time slows down compared to the rest of the universe. In the vicinity of a black hole, the effects of general relativity become extremely pronounced. One of the most striking consequences is gravitational time dilation, the slowing of time in strong gravitational fields. According to Einstein's theory, time passes more slowly in regions of higher gravitational potential. Near the event horizon of a black hole, space-time is curved to such an extreme degree that clocks placed there tick significantly slower than those in weaker gravitational environments. To a distant observer, any object approaching the event horizon appears to move more and more slowly, asymptotically freezing in time as it nears the boundary. From the perspective of the falling object, however, time proceeds normally. This effect is not merely a theoretical prediction. Time dilation due to gravity has been confirmed experimentally on much smaller scales. For instance, atomic clocks placed at different altitudes on Earth tick at slightly different rates due to differences in gravitational potential. In the case of a black hole, the same principle applies, but the magnitude of the effect becomes extreme. Gravitational time dilation near a black hole has practical implications for any orbiting matter or signals emitted from near the horizon. For example, photons climbing out of the gravitational well are redshifted, losing energy and shifting to longer wavelengths. This gravitational redshift has been observed in X-rays emitted from the inner edges of accretion disks around black holes. Time dilation also plays a role in simulations of black hole mergers and interactions, where relativistic corrections must be included to model orbits, waveforms, and timing of gravitational wave emissions. The study of such phenomena provides stringent tests of general relativity in the strong field regime. Fact 9. When black holes collide, they send out ripples in space called gravitational waves. When two black holes orbit each other and eventually merge, they release energy in the form of gravitational waves, disturbances in the curvature of space-time that propagate outward at the speed of light. These waves were first predicted by Albert Einstein in 1916 as part of his general theory of relativity, but their direct detection was not achieved until a century later. The first confirmed observation of gravitational waves occurred in 2015 when the LIGO detectors recorded the signal from a binary black hole merger. This event, known as GW 50914, marked the beginning of gravitational wave astronomy. Since then, numerous additional detections have been made, including mergers involving black holes of various masses and configurations. Gravitational waves are generated by accelerating masses with a quadrupole moment. In the case of black hole mergers, the system emits increasing amounts of gravitational radiation as the two black holes spiral inward. The final moments of the merger release an enormous amount of energy, equivalent to several solar masses, in a fraction of a second. The waveform of a gravitational wave signal carries detailed information about the properties of the merging black holes, such as their masses, spins, and orbital parameters. Analyzing these signals allows researchers to test general relativity in the highly nonlinear, strong gravity regime, and to study the population of black holes in the universe. Unlike electromagnetic waves, gravitational waves are not absorbed or scattered by matter, allowing them to pass through intervening space virtually unimpeded. This makes them ideal for observing phenomena that would otherwise be hidden, such as the final merger stages of compact objects or events occurring in dense, dust-obscured regions of the cosmos. The development of next-generation gravitational wave observatories, such as LISA, a space-based detector, will further expand the observational window and allow detection of lower-frequency waves from supermassive black hole mergers and other exotic systems. Fact 10. Some scientists think black holes could hide doorways to other regions of space. Among the theoretical solutions to Einstein's equations of general relativity are configurations known as wormholes, hypothetical tunnels connecting distant regions of space-time. Some of these solutions resemble the geometry of black holes and suggest that certain types of black holes could act as gateways to other locations or even to other universes. In theory, a wormhole could be formed when a black hole is connected to another point in space or time via a throat. The most commonly discussed model is the Einstein-Rosen bridge, which links two separate space-time regions via a Schwarzschild black hole. However, such bridges are not traversable in their simplest form because they collapse too quickly for matter to pass through. More complex models, such as those involving charged or rotating black holes, Reissner-Nordstrom or Kerr solutions, allow for the theoretical possibility of extended passageways. Yet, these models often require conditions that may not exist in the real universe, such as the presence of exotic matter with negative energy density to stabilize the wormhole and prevent its collapse. Although there is currently no observational evidence for traversable wormholes or connected regions through black holes, the idea remains an intriguing avenue for theoretical research. It serves as a testing ground for quantum gravity and for the reconciliation of general relativity with quantum mechanics. In addition, ongoing research into the internal structure of black holes, including the firewall paradox and the holographic principle, continues to challenge and refine our understanding of what lies beyond the event horizon. These efforts aim to determine whether the singularity at a black hole's center represents a physical endpoint or a placeholder for yet-to-be-discovered physics. While black holes are known to be powerful gravitational objects, their internal structure remains inaccessible to current observations. Theoretical explorations of possible connections to other regions of spacetime offer a frontier for future inquiry. Chapter 5. The Nature of Time. Fact 1. Time moves more slowly in strong gravitational fields, like near a planet or star. Gravitational time dilation is a well-established consequence of Einstein's general theory of relativity. It states that time passes more slowly in stronger gravitational fields compared to regions with weaker gravity. This phenomenon has been experimentally verified and is relevant not only in extreme cosmic environments but also in everyday applications such as satellite-based navigation systems. The underlying cause of gravitational time dilation lies in the curvature of spacetime around massive objects. General relativity describes gravity not as a force in the classical sense, but as the warping of spacetime caused by mass and energy. In regions close to a massive object, such as a planet, star, or black hole, spacetime is significantly curved. As a result, the passage of time is affected. This effect becomes more pronounced as one moves closer to the mass generating the gravitational field. For example, time moves slightly more slowly on the surface of Earth than it does at higher altitudes. Although this difference is minuscule, on the order of nanoseconds, it has measurable consequences. The Global Positioning System, GPS, for instance, must account for gravitational time dilation. GPS satellites orbit at higher altitudes where Earth's gravitational pull is weaker. Without relativistic corrections, GPS positional accuracy would degrade rapidly. In stronger gravitational environments, such as near neutron stars or the event horizon of a black hole, time dilation becomes much more significant. An observer near such an object would experience time at a dramatically slower rate compared to a distant observer. This leads to effects such as gravitational redshift, where light emitted from a region of strong gravity appears shifted to longer wavelengths when observed from a distance. Gravitational time dilation has been confirmed through several experiments. In 1976, the Gravity Probe. The mission carried a hydrogen maser atomic clock to a height of over 10,000 kilometers, demonstrating time dilation consistent with the predictions of general relativity. More recently, highly accurate atomic clocks have been used to measure time dilation at altitude differences of just a few centimeters. Fact 2. Traveling at high speeds also makes time pass more slowly for the traveler. Time dilation also occurs as a result of relative motion, a consequence of Einstein's special theory of relativity. According to this theory, time does not pass at the same rate for all observers. When one observer moves at a significant fraction of the speed of light relative to another, the moving observer's clock ticks more slowly from the perspective of the stationary observer. This form of time dilation is known as kinematic or velocity-based time dilation. It becomes appreciable only at velocities approaching the speed of light. The relationship between velocity and time dilation is described by the Lorentz factor, which increases dramatically as the velocity of an object approaches the speed of light. At these high speeds, the difference in the passage of time becomes increasingly noticeable. This concept has been confirmed in a variety of experiments. One of the most well-known involves muons, short-lived subatomic particles produced when cosmic rays strike Earth's atmosphere. Muons decay rapidly, with a mean lifetime of about 2.2 microseconds when at rest. However, muons traveling at relativistic speeds toward the Earth's surface are observed to survive significantly longer than expected. This is because, from the perspective of the Earth-based observer, time passes more slowly for the high-speed muons, allowing them to reach the surface before decaying. Another confirmation comes from experiments involving atomic clocks flown on high-speed aircraft or placed aboard orbiting satellites. When synchronized atomic clocks are compared after one experiences high-speed motion, they show measurable discrepancies due to time dilation, consistent with special relativity. This form of time dilation is a critical factor in high-energy particle physics, space travel planning, and the design of satellite systems. As with gravitational time dilation, it reflects the relative nature of time and highlights the need for relativistic physics in understanding motion and synchronization. Fact 3. If one twin traveled to space near light speed and came back, they'd be younger than the other. This scenario, often referred to as the twin paradox, is a thought experiment used to illustrate the effects of time dilation under special relativity. It describes a situation in which one twin travels on a high-speed journey through space, while the other remains on Earth. Upon returning, the traveling twin is younger than the twin who stayed behind. Despite being called a paradox, this outcome is fully consistent with the principles of special relativity. The apparent contradiction arises from the assumption that time dilation should be symmetrical, that if one twin sees the other's clock ticking slowly, the effect should be mutual. However, the resolution lies in the fact that the traveling twin undergoes acceleration and deceleration, breaking the symmetry of the situation. In the frame of the Earth-bound twin, the traveling twin moves at relativistic speeds and experiences less proper time. The time experienced by the traveling twin depends on the duration and speed of the journey, with greater time dilation occurring as speed approaches the speed of light. The longer and faster the trip, the greater the age difference upon return. This scenario has been modeled mathematically and aligns with the predictions of time dilation derived from the Lorentz transformations. Although it has not been demonstrated on human scales due to current technological limitations, similar relativistic time discrepancies have been observed in the behavior of subatomic particles and atomic clocks, as discussed earlier. The twin paradox remains a useful tool in physics education to illustrate the non-intuitive but experimentally validated effects of relativistic motion on the passage of time. It also serves as a theoretical consideration for future space travel, where long-duration, high-speed missions could lead to measurable age differences between astronauts and those remaining on Earth. Fact 4. A second is measured using the vibrations of atoms. The definition of time, and specifically of the second, is based on atomic processes that are highly stable and reproducible. Modern timekeeping relies on atomic clocks, which use the natural oscillations of atoms as a frequency standard. The most commonly used atom for this purpose is cesium-133. In 1967, the International System of Units, SI defined the second as the duration of exactly 9,192,631,770 cycles of the radiation, corresponding to the transition between two hyperfine energy levels of the ground state of the cesium-133 atom. This definition provides an incredibly precise and consistent unit of time measurement. Atomic clocks operate by measuring the frequency of microwave radiation absorbed or emitted by cesium atoms as they transition between these energy levels. The stability and accuracy of these clocks are such that they would lose or gain less than a second over millions of years. Other types of atomic clocks use different atoms, such as rubidium or hydrogen, and more recently, optical lattice clocks based on strontium or ytterbium have been developed, offering even higher precision. These precise timekeeping standards are essential for a wide range of applications. Global navigation satellite systems, such as GPS, rely on the synchronization of multiple atomic clocks aboard satellites to provide accurate positioning data. Telecommunications, network synchronization, and scientific research all depend on accurate timekeeping. Efforts are ongoing to redefine the second based on optical frequencies, which offer higher stability than microwave transitions. Optical atomic clocks have demonstrated the potential to achieve accuracy improvements by several orders of magnitude, and work is underway to ensure consistency and reproducibility across international standards. Fact 5. Time appears to flow in one direction, largely because of increasing disorder. The observed directionality of time, from past to future, is known as the arrow of time. While the fundamental physical laws governing microscopic interactions are mostly time-symmetric, meaning they work equally well forward or backward in time, the macroscopic world exhibits a clear temporal asymmetry. The primary explanation for this asymmetry lies in the second law of thermodynamics. This law states that in a closed system, the total entropy, a measure of disorder or randomness, tends to increase over time. As systems evolve toward thermodynamic equilibrium, they move from states of lower entropy to states of higher entropy. This trend provides a statistical basis for the apparent one-way flow of time. Entropy can be illustrated by a variety of examples: a cup of hot coffee cooling to room temperature, a gas spreading out to fill a container, or a broken object not spontaneously reassembling. These processes are overwhelmingly more likely in the direction of increasing entropy, even though they are not strictly forbidden in reverse. The statistical improbability of entropy decreasing provides the macroscopic arrow of time. The link between entropy and time's direction also influences our understanding of cosmology. The universe began in a state of extremely low entropy, and its ongoing evolution toward higher entropy drives the observed direction of time. The cause of the universe's initial low entropy state remains an open question in theoretical physics. Other arrows of time, such as the psychological arrow, our perception of time moving forward, and the radiative arrow, waves radiating outward from a source, are consistent with and likely emergent from the thermodynamic arrow. Though time-symmetric at the level of most equations in physics, the statistical behavior of large systems ensures that, in practice, time flows in one direction, from lower entropy in the past to higher entropy in the future. Fact 6. Time may have started with the birth of the universe itself. The prevailing cosmological model, the lambda cold dark matter model, CDM, describes a universe that originated approximately 13.8 billion years ago in a state of extremely high temperature and density, an event commonly referred to as the Big Bang. According to this model, not only did matter and energy emerge at this point, but space and time themselves also began to exist. General relativity, which describes the large-scale structure of space-time, allows for solutions in which time has a beginning. When extrapolating backward from the current expansion of the universe using Einstein's field equations, the scale factor approaches zero, suggesting a singularity. a point at which density and curvature become infinite. While this mathematical singularity likely indicates a breakdown of classical physics rather than a literal point, it suggests that time, as we understand it, could not be extended further into the past. In this framework, there is no meaningful concept of before the Big Bang, because time itself did not exist. Events, causality, and temporal intervals only make sense from the moment the universe began expanding. Thus, the origin of the universe marks the beginning of time in physical terms. Alternative models, including those derived from quantum cosmology, attempt to describe the initial conditions without invoking a true singularity. One such model is the Hartle-Hawking no-boundary proposal, which posits that the universe is finite but without a boundary, replacing the singularity with a smooth, curved geometry governed by quantum laws. In such models, time transitions smoothly from an imaginary to a real value, avoiding the need for a temporal starting point in the traditional sense. Despite the speculative nature of these models, the consensus in modern cosmology is that time, as it is measurable and meaningful to physics, began at or near the origin of the universe. This view is consistent with observational evidence such as the cosmic microwave background radiation and the distribution of galaxies, which indicate a universe with a well-defined age and an origin in a hot, dense state. Fact 7. In the world of particles, time behaves differently than in the world of planets and stars. At the quantum scale, the treatment of time diverges from the classical, deterministic picture found in Newtonian mechanics and general relativity. In quantum mechanics, time is treated as an external parameter, continuous, absolute, and unaffected by the system it describes. This is in contrast to general relativity, where time is dynamic and influenced by mass and energy. In non-relativistic quantum mechanics, time serves as a parameter that dictates the evolution of the wave function through the Schrödinger equation. The wave function, which encodes the probability amplitudes of a system's possible states, changes over time according to this deterministic equation. However, the outcome of any measurement is probabilistic, not deterministic, and the concept of when a particle takes on a definite state becomes ambiguous. Furthermore, quantum entanglement introduces non-local correlations between particles that seem to defy classical temporal ordering. Measurements performed on entangled particles appear to affect each other instantaneously, regardless of distance. While this does not violate causality or allow for faster-than-light communication, it challenges classical intuitions about time and sequence. In relativistic quantum field theory, the reconciliation of special relativity in quantum mechanics requires that time and space be treated on equal footing as part of a unified space-time framework. Here, events are described using 4 vectors, and particles are understood as excitations in underlying quantum fields. Time remains a background parameter, but its treatment is more symmetrical with spatial dimensions. Efforts to unify quantum mechanics and general relativity, most notably in quantum gravity theories such as string theory and loop quantum gravity, have led to proposals where time itself may be an emergent property rather than fundamental. In these models, space-time arises from more basic entities or structures, and time may lose its conventional meaning at the Planck scale. These quantum behaviors underscore the need for a consistent theory of quantum gravity to fully understand the nature of time across all physical scales. Fact 8. Spacecraft must account for changes in time to stay accurate when using satellites. Satellite-based navigation systems, such as the Global Positioning System, GPS, rely on extremely precise timekeeping to determine positions on Earth. These systems use a constellation of satellites equipped with atomic clocks, which continuously broadcast timing signals. A receiver on Earth calculates its location by measuring the time delay between receiving signals from multiple satellites. However, the clocks on these satellites are subject to both special and general relativistic time dilation. GPS satellites orbit Earth at an altitude of approximately 20,200 kilometers and travel at speeds of about 14,000 kilometers per hour. Due to their velocity, special relativity predicts that time on the satellites should run slightly slower than on Earth's surface. This effect causes a time loss of about 7 microseconds per day. Simultaneously, the weaker gravitational field at the altitude of GPS satellites causes time to run faster relative to clocks on Earth, as predicted by general relativity. This effect leads to a time gain of about 45 microseconds per day. When combined, the net result is that satellite clocks tick about 38 microseconds per day faster than those on the ground. Although this discrepancy may appear small, it would result in navigation errors of several kilometers per day if not corrected. Therefore, GPS systems must include relativistic corrections in their algorithms to maintain accuracy. The onboard clocks are pre-calibrated and additional real-time corrections are continuously applied by the control segment on Earth. This practical application of relativistic time dilation serves as one of the most compelling real-world demonstrations of Einstein's theories. It illustrates that accurate timekeeping and synchronization in modern technology require the integration of both special and general relativity. Similar considerations apply to other satellite systems such as GLONASS, Galileo, and Beidou. In each case, accounting for relativistic time effects is essential for ensuring precise positioning, timing, and navigation services across the globe. Fact 9. At extremely tiny scales, time may not behave the way we expect. At the Planck scale, approximately 10 - 35 tenths - 35 10 - 35 meters in length, and 10 - 43 10 squen is 43 10 - 43 seconds in time. Quantum effects dominate, and classical descriptions of space-time may no longer be valid. In this regime, the smooth fabric of space-time envisioned by general relativity is thought to break down into a fluctuating probabilistic structure. Quantum fluctuations in both space and time are expected to become significant at this scale. These fluctuations, often visualized as quantum foam, imply that space-time itself is subject to uncertainty and lacks a well-defined structure. Time intervals shorter than the Planck time may not be physically meaningful, and standard concepts of causality and temporal order may require modification. Various theoretical models attempt to describe physics at the Planck scale. In loop quantum gravity, for example, space-time is quantized, and both area and volume have discrete values. In this framework, time may also emerge from more fundamental relations among quantum states rather than being an independent parameter. String theory, another candidate for a theory of quantum gravity, replaces point-like particles with one-dimensional strings whose vibrations correspond to different particles. Time in string theory is embedded in higher-dimensional space-time and may be affected by dualities and topological properties that alter our understanding of temporal evolution. One of the challenges in this area is the absence of empirical data. The energies required to probe Planck-scale physics are far beyond current experimental capabilities. However, indirect observations, such as patterns in the cosmic microwave background or signatures in gravitational wave data, may eventually provide clues. The study of time at these scales is not merely academic. It is crucial for resolving long-standing issues in physics, such as the nature of singularities, the behavior of black holes, and the unification of the fundamental forces. Fact 10. Time does not tick the same everywhere. It depends on speed and gravity. Time in the universe is not absolute. According to the principles of both special and general relativity, the passage of time depends on the observer's velocity and the gravitational environment. This means that identical clocks placed in different conditions, one in motion, another stationary, one near a massive object, another far away, will not remain synchronized. This phenomenon has been demonstrated through a wide range of experimental methods. As previously discussed, high-speed motion results in kinematic time dilation, while gravitational time dilation occurs in strong gravitational fields. Together, these effects mean that time is not uniform throughout the universe. It is relative to each observer's frame of reference. Consider two synchronized atomic clocks. Place one on the ground and send the other aboard a high-altitude aircraft or into orbit. Upon reunion, the moving clock will display a different elapsed time due to the combined effects of gravitational and velocity-based time dilation. These differences, though small, are precisely measurable with modern atomic clocks. Relativistic time discrepancies also affect cosmological observations. Light emitted from distant galaxies billions of years ago experiences redshift due to the expansion of the universe, altering our perception of when events occurred. In highly curved regions of space-time, such as near black holes or neutron stars, the passage of time becomes increasingly distorted. Because time behaves differently across varying conditions, modern physics does not define a single universal time. Instead, time is treated as a local quantity, measured by clocks in specific locations, each influenced by their surroundings. This understanding of time's variability is essential for many areas of science and engineering, including satellite navigation, astrophysics, and fundamental research. It reinforces the principle that time is an integral part of the dynamic, relativistic structure of space-time, rather than a fixed and uniform backdrop. Chapter 6: Cosmic Phenomena and Extreme Events. Fact 1. Some explosions in space release more energy in seconds than our Sun will in its lifetime. Gamma-ray bursts, or GRBs, are among the most powerful and energetic events observed in the universe. These short-lived phenomena can release as much energy in a few seconds as the Sun is expected to emit over its entire 10 billion-year lifetime. They are detectable across vast cosmological distances and are typically observed as intense flashes of gamma radiation. GRBs are categorized into two classes based on their duration and spectral properties: long-duration bursts, which last more than 2 seconds, and short-duration bursts, which last less than 2 seconds. Long GRBs are generally associated with the collapse of massive stars, known as collapsers, while short GRBs are believed to result from the merger of compact objects such as neutron stars. During a long GRB, a rapidly rotating massive star undergoes core collapse and forms a black hole or a neutron star. The collapse triggers the formation of relativistic jets that break through the star's surface and emit gamma rays along narrow cones. If one of these jets is directed toward Earth, it can be observed as a GRB. Short GRBs, on the other hand, originate from the coalescence of two neutron stars, or a neutron star and a black hole. These mergers also generate relativistic jets and release enormous quantities of gamma radiation. Such events are now known to be sources of gravitational waves as well. The energy output of GRBs is primarily concentrated within a narrow jet, meaning the total energy emitted is less than initially assumed when assuming isotropic emission. However, even when corrected for beaming, the energy involved remains immense. Following the initial gamma-ray emission, an afterglow is typically observed at longer wavelengths, such as X-ray, optical, and radio frequencies. The afterglow provides additional information about the environment surrounding the burst and the mechanisms that drive the event. GRBs are detected by space-based observatories such as NASA's SWIFT and Fermi satellites. Due to their brightness and distance, they are valuable tools for probing the early universe, as some GRBs have been detected at redshifts greater than 8, corresponding to a time when the universe was less than 700 million years old. Fact 2. Quasars shine with the light of entire galaxies powered by black holes. Quasars, or quasi-stellar objects, are highly luminous sources of electromagnetic radiation found at the centers of some distant galaxies. Their exceptional brightness can outshine the combined light of all the stars in their host galaxies. Quasars are powered by accretion of matter onto supermassive black holes that lie at galactic centers. The mechanism underlying quasar luminosity involves an accretion disk, a rotating disk of gas and dust that forms around the black hole as material falls inward. As the matter in the disk spirals closer to the event horizon, it becomes heated by friction and compression, reaching temperatures of millions of degrees. This process emits radiation across the electromagnetic spectrum, from radio waves to X-rays. Quasars are most commonly detected at high redshifts, meaning they are observed as they existed in the early universe. Their study has provided critical insights into the formation and growth of supermassive black holes, galaxy evolution, and the ionization history of the intergalactic medium. The term quasar was first used in the 1960s, when astronomers noticed that certain radio sources had optical counterparts that resembled stars, but with extremely unusual spectral features. These spectra revealed high redshifts, implying that the objects were extremely distant and, by extension, extremely luminous. Quasars are a subclass of a broader group known as active galactic nuclei, AGN, which also includes objects such as Seyfert galaxies, blazars, and radio galaxies. The distinguishing feature of a quasar is its extremely high luminosity, often reaching 1044 ET to 1041N41 watts, sustained by accretion processes on scales of light days to light years. Their variability in brightness, sometimes on timescales as short as days, suggests that the emitting regions are relatively compact, further supporting the presence of a central supermassive black hole. Quasar emissions are often accompanied by relativistic jets and strong magnetic fields, adding complexity to their observational signatures. Fact 3. Scientists have detected powerful radio signals from deep space with unknown causes. Fast radio bursts, or FRBs, are brief, intense pulses of radio waves originating from distant regions of the universe. Each burst lasts only a few milliseconds, yet emits as much energy as the sun does in a day. Despite their short duration, FRBs are now known to be a common cosmic phenomenon, with potentially thousands occurring every day across the sky. The first FRB was discovered in 2007 in archival data from the Parkes Radio Telescope in Australia. Since then, many more have been detected by various radio observatories, including CHIME in Canada, the Australian Square Kilometre Array Pathfinder, ASCAP, and the Arecibo Observatory. Some FRBs have been found to repeat, while others are apparently one-time events. The exact mechanisms responsible for FRBs are still under investigation. Proposed sources include magnetars, neutron stars with extremely strong magnetic fields, merging compact objects, and even hypothetical exotic phenomena. In 2020, the first galactic FRB was detected from a known magnetar in the Milky Way, strengthening the case for magnetars as at least one source of these bursts. FRBs are dispersed as they travel through intergalactic space. Lower frequency components of the signal arrive later than higher frequency ones due to interaction with free electrons in the intergalactic medium. This dispersion measure allows astronomers to estimate the distance to the source and to probe the distribution of matter between galaxies. Some repeating FRBs exhibit complex patterns, including periodic activity and polarization changes, which provide clues about their environments. Continued observations aim to identify host galaxies, study emission mechanisms, and improve localization techniques. Despite progress, the full population of FRBs and their underlying causes remain a mystery, making them one of the most active and intriguing research topics in modern astrophysics. Fact 4. Certain stars have magnetic fields trillions of times stronger than Earth's. Magnetars are a type of neutron star characterized by extremely powerful magnetic fields, often exceeding 1,014 Gauss, roughly 1,000,000,000,000 times stronger than the Earth's magnetic field. These objects represent one of the most extreme states of matter in the universe, combining intense gravitational, magnetic, and rotational forces. The magnetic field of a magnetar is thought to arise during its formation in a supernova explosion. If the progenitor star possesses strong magnetic fields and rotates rapidly, a dynamo mechanism may amplify the magnetic field as the core collapses. The resulting magnetar retains this intense field in its compact, highly conductive structure. Magnetars emit high-energy radiation, including X-rays and gamma rays. They are often identified as soft gamma repeaters (SGRs) or anomalous X-ray pulsars (AXPs), depending on their emission characteristics. These designations reflect the diverse observational properties of magnetars across different wavelengths. One of the most notable features of magnetars is their tendency to undergo sudden outbursts or flares. These events are thought to result from magnetic stress in the crust of the neutron star. When magnetic field lines become twisted or reconfigured, they can cause starquakes, fractures in the crust that release enormous amounts of energy in short bursts. The strongest magnetic field ever inferred from a celestial object was from magnetar SGR 1806 Tudu, which produced a flare in 2004 detectable from over 50,000 light-years away. The energy released in less than a second temporarily outshone all other X-ray sources in the sky. Magnetars are relatively rare, with only a few dozen confirmed cases. Their study contributes to understanding the behavior of matter at nuclear densities, magnetic field evolution, and the origins of phenomena like FRBs and high-energy cosmic rays. Fact 5. High-speed particles from space constantly hit Earth's atmosphere. Cosmic rays are high-energy particles that travel through space and strike the Earth's atmosphere. Most of these particles are protons, but they also include atomic nuclei and a small fraction of electrons and positrons. Cosmic rays originate from a variety of astrophysical sources, including the Sun, supernova remnants, neutron stars, and possibly active galactic nuclei. When cosmic rays enter Earth's atmosphere, they collide with atomic nuclei in the air, producing cascades of secondary particles known as extensive air showers. These showers include pions, muons, electrons, and neutrinos, which can be detected at the surface using specialized instruments such as scintillators, Cherenkov detectors, and cloud chambers. Cosmic rays are classified into two main categories: galactic and extragalactic. Galactic cosmic rays originate within the Milky Way, likely accelerated by shock waves from supernova explosions. Extragalactic cosmic rays, especially at ultra-high energies, are believed to come from more distant and powerful sources, although their exact origins remain uncertain. The highest energy cosmic rays are extremely rare, but carry more kinetic energy than a baseball in motion, concentrated in a single atomic nucleus. Cosmic rays pose both opportunities and challenges for science and technology. They provide valuable information about astrophysical processes and particle interactions at energies beyond current accelerator capabilities. However, they can also interfere with electronic systems, damage spacecraft, and present a radiation hazard for astronauts. Research into cosmic rays continues at ground-based observatories such as the Pierre Auger Observatory and space-based platforms like AMS-02 aboard the International Space Station. These studies aim to map the spectrum, composition, and arrival directions of cosmic rays to better understand their sources and propagation through space. Fact 6. Some supernovae are so energetic they are called hypernovae. A hypernova is an exceptionally energetic type of supernova that releases significantly more energy than typical core collapse supernova. These events are linked to the deaths of very massive stars and are considered one of the leading candidates for producing long-duration gamma-ray bursts. GRBs. Hypernovae are thought to occur when stars with initial masses exceeding 30 to 40 times that of the Sun exhaust their nuclear fuel and undergo core collapse. Instead of producing a neutron star, the core collapses directly into a black hole. The outer layers of the star are then ejected in a highly energetic explosion. The extreme energies involved can drive relativistic jets, which, if aligned with Earth, are observed as GRBs. A well-studied example is SN 1998 BW, which was associated with GRB 980425. This event provided one of the first clear connections between hypernova and GRBs, suggesting that some long GRBs are indeed caused by such powerful stellar explosions. Subsequent observations of other GRB-associated supernovae have strengthened this link. Theoretical models propose that a rapidly rotating core with a strong magnetic field can facilitate the formation of jets during collapse. This is known as the collapsor model, and it helps explain the asymmetric structure and high kinetic energy observed in hypernova remnants. Hypernovae are rare events and are typically found in star-forming galaxies, especially in regions with low metallicity. This low metallicity reduces mass loss through stellar winds, allowing stars to retain more mass and angular momentum, two critical factors for producing a hypernova. Observationally, hypernovae are distinguished by their high peak luminosity, broad spectral lines indicating high expansion velocities, and the association with GRBs. These events provide critical insights into massive star evolution, nucleosynthesis of heavy elements, and the conditions required to produce relativistic outflows. Fact 7. Jets from distant galaxies sometimes shoot directly toward Earth. In some active galaxies, particularly those classified as blazars, relativistic jets of charged particles are emitted from the vicinity of a supermassive black hole and are directed nearly along our line of sight. These jets can extend across intergalactic distances and emit radiation over a broad range of frequencies, from radio waves to gamma rays. The core engine behind these jets is believed to be the accretion of matter onto a rotating supermassive black hole. As material spirals into the black hole, magnetic fields become twisted and intensified, collimating and accelerating charged particles along the rotational axis of the black hole. The resulting jets move at speeds close to that of light and can remain stable over millions of years. When one of these jets points directly at Earth, the object is classified as a blazar. Blazars are a type of active galactic nucleus, AGN, and are among the brightest and most variable sources in the sky. The relativistic motion of the jet toward Earth leads to Doppler boosting, which enhances the observed luminosity and compresses timescales of variability. Blazars are characterized by rapid variability, high polarization, and a spectral energy distribution with two broad peaks. The lower energy peak is attributed to synchrotron radiation from relativistic electrons spiraling in magnetic fields, while the higher energy peak is typically caused by inverse Compton scattering or hadronic processes. Multi-wavelength observations, including radio, optical, X-ray, and gamma-ray telescopes, are essential for understanding jet composition, particle acceleration mechanisms, and magnetic field configurations. Facilities such as the Fermi Gamma Ray Space Telescope, Very Long Baseline Array, VLBA, and the MAGIC and Veritas observatories have all contributed to blazar studies. These jets can also impact their surroundings, depositing energy into the intergalactic medium and regulating star formation in the host galaxy. As such, blazars and their jets are not only spectacular astrophysical phenomena, but also play a role in galaxy evolution and feedback mechanisms. Fact 8. When a star gets too close to a black hole, it can be torn apart in seconds. Tidal disruption events, TDEs, occur when a star ventures too close to a supermassive black hole and is pulled apart by tidal forces. These forces arise from the difference in gravitational pull across the star's diameter. As the star approaches the black hole's tidal radius, the differential forces exceed the star's self-gravity, leading to its destruction. The process begins as the star is stretched into an elongated shape. It then undergoes partial or complete disruption depending on its initial mass, trajectory, and the black hole's mass. Roughly half of the star's material becomes unbound and is ejected into space, while the other half falls back toward the black hole, forming an accretion disk. The sudden accretion of stellar debris onto the black hole produces a luminous flare, observable across ultraviolet, optical, and X-ray wavelengths. The peak luminosity can exceed that of an entire galaxy for a brief period, followed by a gradual decline over weeks to months. This emission profile is a key signature for identifying TDEs. TDEs are valuable astrophysical laboratories for studying the dynamics of black hole accretion and relativistic effects near event horizons. They provide a unique opportunity to detect otherwise dormant supermassive black holes in galactic centers. Because most galaxies do not exhibit continuous AGN activity, TDEs can serve as temporary signposts of black hole presence. Theoretical modeling of TDEs involves solving hydrodynamic equations under extreme gravity and incorporating general relativistic corrections. Observational campaigns, including the Zwicky Transient Facility, ZTF, Pan-STARRS, and eROSITA, are now systematically searching for TDEs by monitoring large swaths of the sky for transient events. Spectroscopic analysis of TDEs can reveal outflows, ionization states, and changes in emission line profiles over time, offering insights into the immediate environment around black holes. Fact 9. The Sun occasionally releases massive bursts of radiation and particles. Solar flares are sudden releases of energy in the Sun's atmosphere, resulting in the emission of electromagnetic radiation across a wide spectrum, from radio waves to X-rays and gamma rays. These flares occur in regions of intense magnetic activity, particularly near sunspots, where magnetic field lines become twisted and unstable. The energy stored in these magnetic fields is suddenly released through a process called magnetic reconnection. This event accelerates charged particles and heats plasma to tens of millions of degrees Kelvin. The result is a brightening in the solar atmosphere and the emission of energetic photons. Solar flares are classified based on their X-ray intensity in the 1 to 8 angstrom wavelength band, as measured by satellites like GOES. The categories range from A-class, weakest, to X-class, strongest, with each letter representing a tenfold increase in energy output. Accompanying some solar flares are coronal mass ejections, CMEs, massive eruptions of solar plasma and magnetic fields into space. While solar flares emit primarily electromagnetic radiation, CMEs involve the actual expulsion of matter and can interact with Earth's magnetosphere. When directed toward Earth, solar flares and CMEs can disrupt satellite communications, interfere with GPS signals, and pose hazards to astronauts. They also induce geomagnetic storms, which can affect power grids and produce auroras at high latitudes. Monitoring solar activity is critical for space weather forecasting. Observatories such as NASA's Solar Dynamics Observatory (SDO), SOHO, and Parker Solar Probe continuously monitor the Sun's surface and outer atmosphere to track flare development and understand magnetic field evolution. Studying solar flares enhances our knowledge of plasma physics, energy transport, and the interaction between magnetic fields and conductive fluids. These principles have applications not only in astrophysics, but also in fusion energy research and space mission planning. Fact 10. Strong solar storms can affect satellites and power grids on Earth. When coronal mass ejections from the Sun reach Earth, they interact with the planet's magnetic field, sometimes triggering geomagnetic storms. These storms are large-scale disturbances in Earth's magnetosphere that result from the coupling of solar wind and interplanetary magnetic field, IMF, with Earth's own magnetic field. Geomagnetic storms are quantified using indices such as the KP index, which measures fluctuations in Earth's magnetic field, and the DST index, which reflects changes in the ring current. Storms can range in severity from minor to extreme, depending on the strength of the incoming CME and its orientation. One of the most direct consequences of geomagnetic storms is the induction of electric currents in conductive structures on Earth's surface. These geomagnetically induced currents, GICs, can enter power grids, pipelines, and undersea cables, potentially damaging transformers and disrupting operations. The 1989 Hydro-Quebec blackout in Canada, caused by a severe geomagnetic storm, is a notable example. Satellites are also vulnerable to solar storms. High-energy particles can degrade solar panels, cause malfunctions in onboard electronics, and alter satellite orbits by increasing atmospheric drag in low Earth orbit. Radiation exposure is a concern for astronauts, particularly during extravehicular activity or missions beyond Earth's magnetosphere. To mitigate these effects, space weather forecasting agencies such as NOAA's Space Weather Prediction Center and ESA's Space Weather Coordination Center monitor solar activity and issue alerts. Operational responses may include placing satellites into safe mode, delaying launches, or adjusting power grid configurations. Advances in heliophysics have improved models of CME propagation, solar wind behavior, and magnetosphere-ionosphere coupling. However, predicting the exact impact of solar storms remains complex due to the variability of interplanetary conditions and Earth's magnetic response. Understanding and preparing for solar storms is essential for the protection of technological infrastructure and the safety of space-based assets in an increasingly satellite-dependent world. Chapter 7. The Solar System in Detail. Fact 1. Mercury experiences temperature swings of hundreds of degrees between day and night. Mercury, the innermost planet in the solar system, exhibits the most extreme temperature fluctuations of any major planetary body. These temperature variations are primarily the result of the planet's lack of a substantial atmosphere and its slow rotation period relative to its orbital period. During the Mercurian day, surface temperatures can reach up to 430 degrees Celsius, about 800 degrees Fahrenheit. In contrast, nighttime temperatures can plummet to 180 degrees Celsius, kind of 290 degrees Fahrenheit. This represents a swing of more than 600 degrees Celsius between the hottest and coldest surface conditions. One of the key contributors to these extreme changes is the absence of a significant atmosphere. Unlike Earth or Venus, Mercury lacks a dense gaseous envelope capable of distributing heat across the surface. The planet's atmosphere is best described as an exosphere, a tenuous cloud of atoms and molecules that are gravitationally bound but too sparse to behave like conventional gas. Additionally, Mercury's rotational period is quite long. It takes approximately 58.6 Earth days to complete one rotation, while its orbital period around the Sun is just 88 Earth days. This creates a unique 3.2 spin-orbit resonance, meaning the planet rotates 3 times for every 2 orbits it completes. As a result, one solar day on Mercury, the time from one sunrise to the next, lasts about 176 Earth days. Because of this slow rotation, the surface experiences prolonged exposure to sunlight, allowing temperatures to rise dramatically during the day. Conversely, when the surface is turned away from the sun, it remains in shadow for extended periods, allowing it to radiate heat away into space and cool rapidly. Despite its proximity to the sun, Mercury is not the hottest planet in the solar system. That title belongs to Venus. Mercury's temperature extremes are a direct consequence of its rotational dynamics, surface composition, and lack of atmospheric insulation. Fact 2. Venus spins so slowly that a day lasts longer than its year. Venus presents one of the most unusual rotational characteristics in the solar system. The planet has an extremely slow and retrograde rotation, meaning it rotates in the opposite direction of most other planets, including Earth. Venus takes approximately 243 Earth days to complete a single rotation on its axis, but it only takes about 225 Earth days to complete one orbit around the Sun. As a result, a single day on Venus, measured from one sunrise to the next, is actually longer than a Venusian year. Moreover, due to the retrograde motion, the Sun would appear to rise in the west and set in the east if one were standing on the planet's surface. Venus's slow rotation has several effects on its atmospheric dynamics and thermal environment. Despite the slow planetary rotation, the Venusian atmosphere exhibits extremely fast zonal winds, often referred to as superrotation. These winds can circulate the atmosphere around the planet in just a few Earth days, vastly outpacing the rotation of the solid surface. This atmospheric superrotation plays a major role in redistributing heat, helping to maintain relatively uniform temperatures across the planet's surface. The thick carbon dioxide-rich atmosphere, combined with clouds of sulfuric acid, traps heat efficiently through a runaway greenhouse effect, making Venus the hottest planet in the solar system. Surface temperatures average around 465 degrees Celsius, 869 degrees Fahrenheit, hot enough to melt lead. Venus's unusual rotation is not fully understood. Theories suggest that early impacts, tidal interactions with the Sun, or internal redistribution of mass may have contributed to its present-day state. The planet's retrograde spin and extremely slow rotation challenge models of planetary formation and evolution, and they remain active areas of research. Fact 3. Earth is currently the only known world to support life and liquid oceans. Earth occupies a unique position in the solar system as the only planet confirmed to support life. Its biosphere is sustained by a combination of favorable factors, including its position within the Sun's habitable zone, the presence of liquid water, a protective atmosphere, and a dynamic geological system. The planet's surface is approximately 71% covered by water, with oceans playing a vital role in climate regulation, nutrient transport, and biological productivity. Water exists in all three phases, liquid, solid, and gas, creating a dynamic hydrological cycle that interacts with the atmosphere and biosphere. Earth's atmosphere is composed primarily of nitrogen and oxygen, with trace amounts of carbon dioxide, water vapor, and other gases. This atmosphere not only provides essential gases for respiration and photosynthesis, but also acts as a shield against harmful solar and cosmic radiation. The ozone layer, in particular, absorbs ultraviolet radiation, protecting living organisms at the surface. The planet's magnetic field, generated by the motion of molten iron in the outer core, extends far into space and forms the magnetosphere. This magnetic shield deflects charged particles from the solar wind, reducing atmospheric erosion and contributing to the planet's long-term habitability. Earth's plate tectonics facilitate carbon recycling, nutrient cycling, and the maintenance of surface environments conducive to complex life. Volcanism, mountain building, and seafloor spreading contribute to geological diversity and support ecosystems that extend from ocean trenches to mountain peaks. From a planetary science perspective, Earth serves as a reference model for evaluating the potential habitability of other planets and moons. Its climate, geology, and biosphere provide essential constraints for comparative planetology and guide the search for life elsewhere in the universe. Fact 4. Mars has a volcano taller than Mount Everest and wider than France. Olympus Mons is the largest known volcano in the solar system, located on Mars in the Tharsis volcanic plateau. It stands approximately 21 to 22 kilometers, 13.6 to 13.7 miles, high, nearly 3 times the height of Mount Everest, and spans roughly 600 kilometers, 373 miles in diameter. Its caldera, the summit depression, measures about 80 kilometers across and contains multiple nested collapse craters. Olympus Mons is classified as a shield volcano, characterized by broad, gently sloping sides built up by successive flows of low-viscosity lava. Unlike stratovolcanoes on Earth, which are steep and prone to explosive eruptions, shield volcanoes erupt primarily through effusive lava flows, allowing them to reach massive sizes over extended periods. The extraordinary size of Olympus Mons is attributed to several factors. First, Mars has lower surface gravity than Earth, only about 38%, which allows taller structures to form before collapsing under their own weight. Second, the Martian crust is thicker and more rigid, enabling the accumulation of large volcanic edifices without significant deformation. Additionally, the absence of plate tectonics on Mars means that volcanic hotspots remain stationary relative to the crust. On Earth, plate movement distributes volcanic activity along chains like the Hawaiian Islands. On Mars, a single hotspot can produce a massive, centralized volcano over hundreds of millions of years. Olympus Mons shows evidence of relatively recent volcanic activity, with some lava flows dating back only a few million years. This suggests that Mars may still possess residual geothermal activity, although no current eruptions have been observed. The volcano is surrounded by an escarpment several kilometers high, possibly caused by lava spreading over softer terrain and subsequent collapse. Studies of Olympus Mons and other Tharsis region volcanoes provide insight into the thermal and geological evolution of Mars, including its volcanic history, crustal properties, and potential for past subsurface water reservoirs. Fact 5. Jupiter's magnetic field is incredibly powerful and larger than the Sun. Jupiter possesses the most powerful planetary magnetic field in the solar system. Generated by electrical currents in its interior, this magnetic field extends millions of kilometers into space, creating a magnetosphere that dwarfs even the Sun in size. If it were visible in the night sky, Jupiter's magnetosphere would appear larger than the full moon. The magnetic field is thought to originate from the movement of metallic hydrogen within Jupiter's interior. Under immense pressures exceeding 3 million times Earth's atmospheric pressure, hydrogen behaves like an electrically conductive fluid. Convection and rotation in this metallic hydrogen layer produce a dynamo effect, generating a strong magnetic field. Measurements from spacecraft such as Pioneer, Voyager, Galileo, and Juno have shown that Jupiter's equatorial surface magnetic field strength is about 4.3 Gauss, over 10 times stronger than Earth's. However, the internal field may be substantially stronger, with complex multipolar components detected by Juno's magnetometers. Jupiter's magnetosphere captures and accelerates charged particles, forming intense radiation belts that pose hazards to spacecraft. The interaction between the magnetic field and the solar wind creates a bow shock and extended magnetotail that stretches millions of kilometers away from the Sun. A particularly interesting aspect of Jupiter's magnetosphere is its interaction with its moons, especially Io. Io's volcanic activity injects large amounts of sulfur and oxygen ions into the magnetosphere, forming a torus of plasma around the planet. These charged particles are accelerated by the magnetic field and contribute to powerful auroras near the poles. The Jovian auroras are among the brightest in the solar system and emit ultraviolet and X-ray radiation. They differ from Earth's auroras in that they are partly driven by internal processes, such as the planet's rapid rotation and the dynamics of its moon system, rather than solely by solar-wind interactions. Studying Jupiter's magnetic field enhances our understanding of planetary dynamos, magnetosphere-moon interactions, and space weather effects on large-scale magnetized environments. Fact 6. Saturn's rings are made mostly of water ice and could disappear over time. Saturn's rings are among the most iconic features in the solar system, extending more than 280,000 kilometers from the planet's center, but with an average thickness of only about 10 meters. Composed predominantly of water ice, with a small fraction of rocky debris and dust, the rings reflect significant amounts of sunlight and are easily visible from Earth-based telescopes. The rings are divided into several distinct regions labeled A, B, C, D, E, F, and G rings. The most prominent are the A and B rings, separated by a dark region called the Cassini division. Within each ring are countless particles ranging in size from micrometers to meters. These particles orbit Saturn in nearly perfect circular paths and are held in place by gravitational forces, including interactions with Saturn's moons. Spectroscopic analysis has confirmed that the rings are composed of more than 90% water ice. The high albedo indicates a relatively clean ice surface, although micrometeorite bombardment and interactions with Saturn's magnetosphere gradually introduce contaminants such as silicates and organic materials. Despite their grandeur, Saturn's rings are not permanent. Observations from NASA's Cassini mission have provided evidence that the rings are slowly losing material. Micrometeoroid impacts generate a fine ring rain, in which particles are driven into Saturn's upper atmosphere by the planet's magnetic field. This process, known as ring rain, contributes to the gradual erosion of the rings. Estimates based on Cassini's measurements suggest that Saturn's main ring system may be less than 100 million years old and could disappear entirely within the next 100 to 300 million years. This raises the possibility that we are observing the rings during a transient phase in Saturn's long planetary history. The origin of the rings is still debated. They may have formed from the remnants of a shattered moon or comet that passed within Saturn's Roche limit, the distance within which tidal forces prevent material from coalescing into a larger body. Continued study of ring dynamics, composition, and evolution provides valuable insight into planetary system formation and the behavior of complex orbital systems. Fact 7. Uranus rotates on its side, likely due to a massive impact in the past. Uranus is unique among the planets in that it has an axial tilt of approximately 98 degrees. This means that the planet essentially rolls along its orbital path, with its rotational axis lying nearly in the plane of its orbit. As a result, Uranus experiences extreme seasonal variations, with each pole exposed to continuous sunlight or darkness for over 40 Earth years at a time. The most widely accepted explanation for this unusual axial tilt is a massive collision with a protoplanet-sized object early in the planet's formation. Simulations suggest that an impactor several Earth masses in size could have delivered enough angular momentum to tilt Uranus to its present orientation without destroying the planet's internal structure. This giant impact hypothesis is supported by several lines of evidence. Uranus has a relatively low internal heat flux compared to other gas giants, which may result from the mixing and redistribution of heat caused by such a collision. The planet's magnetic field is also significantly tilted relative to its rotational axis and is offset from the planet's center, features that may reflect a disrupted internal structure. The orientation of Uranus's moons and ring system provides additional support. Most of the planet's regular moons orbit in the plane of its equator, which is itself highly inclined relative to the solar system's ecliptic plane. This alignment suggests that the moons formed or reaccreted after the tilt event, rather than preserving an original configuration. Despite being classified as a gas giant, Uranus is more accurately described as an ice giant. Its composition includes a higher proportion of water, ammonia, and methane ices, mixed with hydrogen and helium. The planet's blue-green coloration is due to methane in its atmosphere, which absorbs red light and reflects blue wavelengths. Understanding Uranus's axial tilt provides insight into the dynamics of planetary formation and the role of giant impacts in shaping planetary evolution. It also raises questions about how similar collisions might influence exoplanets in other star systems. Fact 8. Neptune has the fastest winds in the solar system. Neptune, the 8th planet from the Sun, possesses the most powerful atmospheric winds observed in the solar system. Wind speeds on Neptune have been measured at velocities exceeding 2,000 kilometers per hour, about 1,200 miles per hour. These supersonic winds are found at various latitudes and altitudes within the planet's dynamic atmosphere. The high wind speeds are particularly surprising given the relatively low amount of solar energy Neptune receives, less than 3% of the sunlight that reaches Earth. This suggests that the planet's weather systems are driven by internal heat rather than external solar input. Neptune emits about 2.6 times more energy than it receives from the Sun, indicating the presence of a significant internal heat source. The mechanism for this heat generation remains uncertain, but may involve the gradual release of gravitational potential energy or latent heat from phase transitions in the planet's interior. The atmospheric structure of Neptune consists of several distinct layers. The upper atmosphere contains methane, which absorbs red light and contributes to the planet's striking blue appearance. Below this lies a region of hydrogen, helium, and more methane, with cloud layers composed of ammonia, hydrogen sulfide, and possibly water ice. Observations from the Voyager 2 spacecraft and Earth-based telescopes have revealed a variety of storm systems and cloud features. One of the most notable was the Great Dark Spot, a massive anticyclonic storm comparable in size to Earth. Although it later disappeared, similar features have continued to be observed, indicating a highly active atmosphere. The strong winds are believed to result from a combination of rapid rotation, convection driven by internal heat, and complex atmospheric chemistry. Neptune completes one rotation in about 16 hours, contributing to the Coriolis effect that organizes atmospheric flows into bands and vortices. Studying Neptune's atmospheric dynamics helps researchers model fluid behavior under extreme conditions and provides comparative data for understanding the atmospheres of other giant planets and exoplanets. Fact 9. Pluto has mountains of ice and a heart-shaped glacier bigger than Texas. Although reclassified as a dwarf planet in 2006, Pluto remains one of the most geologically interesting objects in the solar system. The New Horizons mission, which performed a flyby in July 2015, provided the first high-resolution images and data of Pluto's surface and atmosphere, revealing features that were unexpected for a small, distant world. One of the most striking features is Tombaugh Regio, a large, bright, heart-shaped region spanning over 1,500 kilometers. The western lobe of this feature, known as Sputnik Planitia, is a vast nitrogen ice glacier that is larger than the state of Texas. This glacier exhibits a polygonal surface pattern, interpreted as evidence of convection cells caused by slow overturning of ice due to internal heat. Surrounding Sputnik Planitia are rugged mountain ranges composed not of rock but of water ice. Given Pluto's frigid temperatures, averaging around 230 degrees Celsius, and 382 degrees Fahrenheit, water ice behaves like bedrock, forming stable geological structures. The mountains rise several kilometers high and appear to be relatively young, geologically speaking. Pluto's surface is also marked by plains, pits, troughs, and possible cryovolcanoes. These features suggest that the dwarf planet is geologically active and may still possess a subsurface ocean. Models of Pluto's thermal evolution support the possibility that radioactive decay of elements in the core could maintain liquid water beneath the icy crust. Pluto's tenuous atmosphere, composed primarily of nitrogen with trace amounts of methane and carbon monoxide, exhibits seasonal variation and interaction with surface ices. As Pluto moves along its elliptical orbit, solar heating causes the atmosphere to expand or contract, leading to dynamic atmospheric behavior despite the thin air pressure. The complex surface geology and atmospheric dynamics of Pluto challenge prior assumptions about small icy bodies and continue to inform models of planetary evolution, cryovolcanism, and outer solar system processes. Fact 10. Comets are icy bodies, that leave glowing trails when they near the sun. Comets are small solar system bodies composed primarily of volatile ices mixed with dust and rocky material. When a comet approaches the inner solar system, solar radiation heats the nucleus, causing sublimation of ices and the formation of a coma, a glowing cloud of gas and dust surrounding the nucleus. This outgassing also creates one or more tails that can stretch millions of kilometers. The ion tail, made of charged particles, is directed away from the sun by the solar wind, while the dust tail is shaped by both solar radiation pressure and the comet's motion. These tails give comets their characteristic appearance and make them observable from Earth when they are near perihelion. Comet nuclei are typically only a few kilometers across and have irregular shapes. They originate from two primary reservoirs: the Kuiper belt, which lies beyond Neptune, and the Oort cloud, a hypothetical spherical shell of icy bodies extending up to 100,000 astronomical units from the Sun. Comets from the Kuiper belt are known as short-period comets, while those from the Oort cloud are long-period comets. Cometary orbits are often highly eccentric, bringing them close to the Sun before swinging them back into deep space. Some comets, such as Halley's Comet, are periodic and return at predictable intervals. Others may only pass through the inner solar system once before being ejected or colliding with a planetary body. Scientific missions such as ESA's Rosetta, which orbited Comet 67P Churyumov-Gerasimenko, have provided detailed insights into cometary composition, structure, and activity. These missions reveal that comets contain complex organic molecules and may have played a role in delivering water and prebiotic compounds to early Earth. The study of comets enhances our understanding of the primordial solar system, as these bodies preserve materials from the solar nebula that formed over 4.6 billion years ago. Chapter 8: Galaxies and Galactic Dynamics. Fact 1. Our Milky Way is a barred spiral galaxy with hundreds of billions of stars. The Milky Way galaxy, which includes the solar system, is classified as a barred spiral galaxy. This structural classification is based on both morphological observations and dynamic modeling of the galaxy's stellar and gaseous components. A barred spiral galaxy features a central bar-shaped structure composed of stars from which spiral arms extend outward. Current estimates place the number of stars in the Milky Way between 100 billion and 400 billion. This large uncertainty arises due to observational limitations, particularly when viewing toward the densely packed galactic center, where interstellar dust obscures visible light. Infrared and radio observations from telescopes like Spitzer and ALMA help penetrate this dust and provide better star counts. The galaxy's spiral arms are sites of active star formation and contain a high concentration of gas, dust, and young, luminous stars. These arms are not static structures, but rather density waves, regions where stars and gas are temporarily compressed as they orbit the galactic center. This compression leads to gravitational collapse of gas clouds and the formation of new stars. The Milky Way's central bar is thought to rotate as a rigid structure and plays a crucial role in funneling gas from the spiral arms toward the galactic core, potentially fueling star formation and the activity of the central supermassive black hole, Sagittarius A star. The galaxy's disk is approximately 100,000 light-years in diameter and contains both population 1 stars, young, metal-rich stars found mainly in the disk and arms, and older population 2 stars which dominate the galactic bulge and halo. Above and below the disk is the halo, a roughly spherical region containing old globular clusters and dark matter. The Milky Way's rotation curve, which plots orbital velocity versus radius, remains relatively flat at large distances from the center. This observation is one of the key indicators of dark matter, as the visible mass cannot account for the gravitational forces required to maintain such high orbital velocities. Fact 2. Galaxies can collide and merge, reshaping their structure over billions of years. Galactic collisions are a fundamental aspect of galaxy evolution. Although galaxies are composed of vast numbers of stars, the distances between individual stars are so great that direct stellar collisions are rare. Instead, gravitational interactions during a collision lead to large-scale distortions, mergers, and the redistribution of gas, dust, and dark matter. When two galaxies approach each other, their mutual gravitational attraction causes tidal forces that distort their shapes. These tidal interactions can trigger starbursts, intense periods of star formation, by compressing interstellar gas and initiating rapid gravitational collapse. In some cases, the gas may funnel toward the central regions, potentially activating or fueling an active galactic nucleus. Over time, the galaxies may coalesce into a single, larger system. The specific outcome depends on factors such as the mass ratio of the galaxies, their relative velocities, angles of approach, and gas content. Collisions between similarly sized spiral galaxies often result in the formation of elliptical galaxies with randomized stellar orbits and reduced star-forming activity. The Milky Way itself is on a collision course with the neighboring Andromeda galaxy, M31. Simulations suggest the two galaxies will begin to interact in about 4 billion years, culminating in a merger that will reshape both systems. The resulting galaxy is expected to be an elliptical or lenticular galaxy, sometimes referred to as Milkometa in theoretical discussions. Observational evidence of galactic mergers is widespread. The Antennae galaxies are a nearby example of two colliding spiral galaxies exhibiting pronounced tidal tails and starburst regions. Other systems, such as the Tadpole galaxy and the Mice galaxies, show similar features associated with gravitational interaction. These collisions also contribute to the hierarchical formation of galaxies. According to the LUL-CDM cosmological model, large galaxies form through the accumulation and merging of smaller systems over cosmic time. This process plays a central role in shaping galactic morphology and stellar population characteristics. Fact 3. Elliptical galaxies are older, redder, and have little star formation. Elliptical galaxies represent one of the major morphological types in the Hubble sequence and are characterized by their smooth, ellipsoidal shapes and uniform stellar distributions. They are generally devoid of the spiral arms, dust lanes, and active star-forming regions that typify spiral galaxies. Ellipticals span a wide range of sizes and masses, from small dwarf ellipticals to giant ellipticals with trillions of stars. The largest known galaxies by mass are typically giant ellipticals located in the centers of galaxy clusters. These systems are dominated by old, red, low-mass stars, leading to a reddish overall color indicative of aged stellar populations and low rates of ongoing star formation. One of the defining features of elliptical galaxies is their kinematics. Unlike spiral galaxies, which exhibit organized rotational motion, the stars in ellipticals move in random, isotropic orbits. This is indicative of a system that has undergone violent relaxation, a process in which gravitational interactions during mergers redistribute the energy and angular momentum of stars, leading to a stable, spheroidal configuration. Ellipticals also contain little interstellar gas or dust, which limits their ability to form new stars. The lack of cold gas is attributed to past merger events that either consumed the gas through starbursts or expelled it via feedback mechanisms from supernova or active galactic nuclei. As a result, the star formation rates in these galaxies are typically close to zero. Spectroscopic observations confirm that elliptical galaxies contain high fractions of alpha element-enhanced stars, suggesting that their stellar populations formed rapidly in early bursts of star formation. The metallicity gradients within these galaxies also reflect their formation history and subsequent dynamical evolution. In terms of dark matter content, Elliptical galaxies exhibit flat rotation curves and gravitational lensing effects that suggest the presence of substantial dark matter halos, similar to other galaxy types. Fact 4. Spiral galaxies like the Milky Way have rotating arms full of young stars and gas. Spiral galaxies constitute a large portion of observed galaxies and are characterized by their flattened disk structure, central bulge, and well-defined spiral arms. These arms are prominent regions of star formation, containing bright young stars, gas clouds, and dust lanes. The spiral structure is believed to be maintained through a process known as density wave theory. According to this model, the arms are not fixed arrangements of stars, but rather regions of enhanced density that move through the disk like waves. As gas clouds enter these density waves, they are compressed, triggering the formation of new stars. The arms are rich in molecular hydrogen, the primary fuel for star formation, and are often traced using emission from carbon monoxide, a proxy for molecular gas. They are also bright in ultraviolet and H-alpha wavelengths, which correspond to emission from young hot stars and ionized hydrogen regions, respectively. Spiral galaxies are typically classified by the tightness of their arms, the size of the central bulge, and the degree of resolution in their structure. In the Hubble classification, types range from ESA, tightly wound arms, large bulge, to SC, loosely wound arms, small bulge. The Milky Way is classified as a barred spiral, denoted SBB or SBC. The rotation of spiral galaxies provides insight into the distribution of mass, both visible and invisible. Observations of rotation curves. Plots of orbital velocity versus radius show that velocities remain high at large distances from the center, inconsistent with the distribution of luminous matter alone. This discrepancy is one of the primary pieces of evidence for dark matter. Spiral galaxies often have active star-forming disks, but more quiescent bulges. The bulge contains older, redder stars and may host a supermassive black hole, while the disk is the site of ongoing stellar and planetary system formation. Fact 5. Dark matter holds galaxies together and makes them spin faster than expected. Dark matter is an essential component of galaxies, accounting for approximately 85% of their total mass. It does not emit, absorb, or reflect electromagnetic radiation, making it invisible to traditional telescopic observations. Its existence is inferred from gravitational effects on visible matter, particularly the rotational dynamics of galaxies. In spiral galaxies, the rotation curves remain flat or even rise at large radii, well beyond the region where most of the luminous mass is concentrated. According to Newtonian dynamics, one would expect the orbital velocity of stars and gas to decrease with distance from the center if only visible matter were present. The observed discrepancy implies the presence of additional mass that does not emit light. This missing mass is attributed to dark matter, which is thought to form a diffuse, roughly spherical halo enveloping each galaxy. The halo extends well beyond the visible edge of the galaxy and dominates its gravitational potential at large distances. Dark matter also influences the formation and evolution of galaxies. In the LCDM cosmological model, dark matter provides the gravitational scaffolding for the formation of large-scale structure. Overdensities in the early universe, composed primarily of dark matter, attracted baryonic matter, leading to the formation of galaxies and clusters. Gravitational lensing, where the path of light from distant objects is bent by massive foreground structures, provides independent confirmation of dark matter's distribution. Observations of lensing patterns, especially in galaxy clusters, reveal mass concentrations inconsistent with the luminous matter alone. Efforts to directly detect dark matter particles have focused on weakly interacting massive particles, WIMPs, axions, and other theoretical candidates. Although no definitive detection has been made, experiments like Lux Zeppelin and Xenon 1T continue to push sensitivity limits. Dark matter remains one of the central unresolved topics in modern astrophysics, critical not only for understanding galaxy dynamics, but also for the evolution of the universe on the largest scales. Fact 6. Galaxy clusters can contain thousands of galaxies bound by gravity. Galaxy clusters are the largest structures in the universe held together by gravity. These immense systems contain anywhere from a few hundred to several thousand galaxies, along with vast quantities of hot gas and an even greater amount of invisible dark matter. The entire structure stretches across millions of light years and has a combined mass that can be several hundred trillion times the mass of our Sun. The galaxies in a cluster do not just float in empty space. They are surrounded by a hot, diffuse gas known as the intracluster medium. This gas is so hot that it emits X-rays, which astronomers can detect using space-based telescopes. In fact, the mass of this gas exceeds the combined mass of all the stars in the galaxies themselves. The dominant mass in galaxy clusters, however, is dark matter, an invisible substance that does not emit or absorb light, but reveals its presence through gravitational effects. Without this unseen mass, the galaxies in gas would not be gravitationally bound. Clusters are not static. They form over billions of years through the merger of smaller groups of galaxies. When these mergers occur, the hot gas is disturbed, shock waves are produced, and large-scale structures like radio-emitting arcs and filaments can be observed. These features give clues about the cluster's formation history and internal dynamics. By studying clusters, scientists can learn not only about galaxy formation but also about the large-scale structure of the universe, including the distribution of matter and the influence of dark energy. Fact 7. The space between galaxies in clusters is filled with hot gas detectable in X-rays. Between the galaxies in a cluster lies an enormous amount of hot, ionized gas. This gas, known as the intracluster medium, is incredibly thin, far less dense than any vacuum we can produce on Earth, but because of its volume and temperature, it glows brightly in the X-ray part of the electromagnetic spectrum. The temperatures in the intracluster medium are so high that the gas particles are moving at thousands of kilometers per second. This high energy comes from the gravitational forces acting on the gas during the cluster's formation and growth. As gravity pulls material together, it heats up the gas to extreme temperatures. Although invisible in optical light, this gas is one of the most massive components of a galaxy cluster. It holds more ordinary matter than all the stars in the cluster's galaxies combined. Because of this, studying the gas provides a better overall picture of the cluster's structure and mass. X-ray telescopes such as Chandra and XMM Newton are designed to detect this type of emission. Observing the brightness and temperature of the X-ray glow allows scientists to estimate the total mass of the cluster, which includes the dark matter. The distribution of this hot gas also helps researchers understand how clusters grow and interact with their environments. The gas contains traces of heavier elements like iron and silicon that were created in stars and ejected during supernova explosions. Over time, these elements spread into the intracluster medium, turning it into a record of the star formation history of the galaxies within the cluster. Fact 8. Some galaxies shoot out jets of matter at nearly the speed of light. At the centers of many large galaxies are supermassive black holes, and in some cases, these black holes are actively pulling in gas and dust. As this material spirals inward, it forms a hot, spinning disk around the black hole. Magnetic fields in this disk can launch twin jets of particles outward at nearly the speed of light. These jets are among the most powerful structures in the universe. They extend over distances ranging from thousands to even millions of light years, well beyond the edge of the host galaxy. Although the jets are composed of particles much too small to see directly, they emit strong radio waves as well as X-rays and gamma rays. The jets are tightly focused, like beams from a cosmic flashlight, and they carry energy and matter out of the galaxy. Along the way, they can affect surrounding gas and slow down the formation of new stars. When the jets eventually slow down and stop, they create large glowing regions known as radio lobes. These jets don't just form randomly. They are directed by the black hole's spin and the arrangement of magnetic fields in the surrounding material. Observations of galaxies like Centaurus A and M87 have helped astronomers understand how these cosmic engines work. In addition to influencing the host galaxy, these jets play a role in regulating the environment of galaxy clusters. They can heat up nearby gas and prevent it from cooling, which affects how new stars form. This type of feedback helps explain why the biggest galaxies often stop forming new stars and remain quiet for long periods. Fact 9. Gravitational lensing bends light from distant galaxies, making them appear distorted. Gravity doesn't just attract objects, it also bends light. When a massive object like a galaxy or cluster lies between a distant light source and the observer, its gravity can curve the path of light, distorting the appearance of the background object. This effect is called gravitational lensing and is one of the key predictions of Einstein's general theory of relativity. In some cases, gravitational lensing is strong enough to produce dramatic visual effects, such as rings, arcs, or multiple images of the same galaxy. These are known as strong lensing effects. If the alignment between the lens and the background object isn't perfect, the distortions are much subtler. This is called weak lensing, and it can only be seen by looking at the statistical shapes of many background galaxies. There's also a third kind, microlensing, which happens when a single star or planet passes in front of a more distant star, briefly magnifying its light. Gravitational lensing is extremely useful to astronomers. First, it allows them to study galaxies and quasars that would otherwise be too faint to observe. Second, it lets scientists map the invisible dark matter in galaxies and clusters, because the amount of light bending reveals the total mass, not just the visible matter. One of the most famous examples of lensing is the bullet cluster. In this system, the visible matter and the dark matter are clearly separated, giving direct evidence that dark matter exists and behaves differently from ordinary matter during galaxy collisions. With modern space telescopes, lensing has become a tool for studying the early universe, testing cosmological models, and even searching for planets in other star systems. Fact 10. The Milky Way and Andromeda are on a slow-motion collision course. Our home galaxy, the Milky Way, is moving toward the nearby Andromeda galaxy. Although both galaxies are currently separated by more than 2 million light-years, their mutual gravitational pull is bringing them closer together. Despite this enormous distance, measurements show that Andromeda is approaching us at a speed of more than 100 kilometers per second. This motion is not caused by the general expansion of the universe, but by local gravity. The two galaxies are the largest members of the local group, a small family of galaxies bound together by gravity. Eventually, in roughly 4 billion years, the Milky Way and Andromeda will collide and merge to form a single larger galaxy. When this happens, the stars in both galaxies will be rearranged but not destroyed. That's because the stars are spaced so far apart that direct collisions between them are extremely rare. Instead, gravity will stretch and warp the galaxies, creating long tidal tails and new shapes. The collision will also affect the clouds of gas and dust. As these clouds collide and compress, they may trigger new bursts of star formation. Eventually, the merger will settle into a more stable shape, most likely a giant elliptical galaxy with a calmer environment and fewer new stars being born. At the centers of both galaxies are supermassive black holes, and these too will spiral toward each other and eventually merge. That final event will release powerful gravitational waves that ripple through space, potentially detectable with future observatories. This future merger offers astronomers a glimpse into the long-term fate of our galaxy and helps explain how other large galaxies in the universe came to be. Chapter 9: Space Exploration and Technology. Fact 1. The first artificial satellite, Sputnik, launched in 1957, began the space age. The launch of Sputnik 1 by the Soviet Union in October 1957 marked the beginning of the modern space era. It was the first artificial satellite to be placed in Earth's orbit and represented a major technological and geopolitical milestone. Sputnik was a polished metal sphere approximately 2 feet in diameter with 4 external radio antennas. It transmitted a simple radio signal that could be detected around the world. Although it carried no scientific instruments beyond its transmitter, the launch had profound implications. It demonstrated the feasibility of putting objects into orbit, sparked the space race between the United States and the Soviet Union, and shifted the global perception of technological leadership. Sputnik orbited Earth every 96 minutes, and its radio signal, a series of repeated beeps, was monitored by amateur and professional radio operators alike. It remained in orbit for about 3 months before re-entering Earth's atmosphere and burning up. The successful deployment of Sputnik showed that the Soviet Union had developed powerful rocket technology that also had military applications. The response to Sputnik was immediate. In the United States, it led to the rapid development of American space capabilities, including the establishment of NASA in 1958 and increased investment in science and engineering education. The launch also prompted new international discussions about the use of outer space and set the stage for the era of satellites for communication, weather forecasting, Earth observation, and scientific research. From a technical standpoint, Sputnik was simple by today's standards, but it proved critical concepts in orbital mechanics, launch vehicle performance, and spaceflight dynamics. It remains a historical milestone in aerospace engineering and global scientific collaboration. Fact 2. The Apollo missions landed humans on the Moon and returned them safely. NASA's Apollo program was a series of human spaceflight missions undertaken during the 1960s and early 1970s, with the central objective of landing astronauts on the Moon and bringing them back to Earth. The most famous of these missions was Apollo 11, which successfully carried astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins to the Moon in July 1969. The Apollo program was initiated in response to President John F. Kennedy's 1961 goal of achieving a crewed lunar landing before the end of the decade. The project involved thousands of scientists, engineers, and technicians, and required the development of entirely new technologies in rocketry, navigation, life support, and materials engineering. Apollo 11 used the Saturn V launch vehicle, a multi-stage rocket that remains one of the most powerful ever built. It carried the command module, service module, and lunar module, which separated in lunar orbit. Armstrong and Aldrin descended to the Moon's surface in the lunar module, while Collins remained in orbit aboard the command module. During their 2.5 hours on the lunar surface, Armstrong and Aldrin collected rock and soil samples, deployed scientific instruments, and conducted mobility tests. Their safe return to Earth 4 days later demonstrated the success of the mission and established the feasibility of round-trip human travel to another celestial body. In total, 6 Apollo missions landed astronauts on the Moon between 1969 and 1972. These missions greatly expanded our understanding of lunar geology, seismology, and surface conditions. The data and samples returned continue to be analyzed, offering insights into the early history of the solar system. The Apollo program also drove the development of technologies that have had long-lasting impacts, including advances in computing, telecommunications, and aerospace engineering. It remains one of humanity's greatest engineering achievements. Fact 3. Space telescopes avoid Earth's atmosphere, capturing clearer images. Space-based telescopes offer significant advantages over ground-based observatories because they operate above Earth's atmosphere. The atmosphere distorts and absorbs certain wavelengths of light, particularly ultraviolet, X-rays, and parts of the infrared spectrum. By placing telescopes in orbit, scientists can access a broader range of the electromagnetic spectrum and capture sharper images free from atmospheric interference. One of the most successful and widely known space telescopes is the Hubble Space Telescope, launched in 1990. Positioned in low Earth orbit, Hubble has provided high-resolution images of distant galaxies, nebula, star clusters, and exoplanets. It has contributed to major discoveries in cosmology, such as the measurement of the universe's expansion rate and the study of dark energy. Hubble carries multiple scientific instruments, including cameras and spectrographs that operate across ultraviolet, visible, and near-infrared wavelengths. Its mirror, measuring over 7 feet in diameter, allows it to detect faint light from distant sources billions of light-years away. Other space telescopes have been designed to observe specific wavelengths. For example, the Chandra X-ray Observatory observes high-energy phenomena such as black holes and supernova in the X-ray band. The Spitzer Space Telescope, which operated until 2020, specialized in infrared astronomy, revealing details about star formation and planetary systems. More recently, the James Webb Space Telescope, JWST, launched in 2021, has extended the reach of space-based astronomy into the mid-infrared range. With a much larger mirror than Hubble and advanced cooling systems, JWST allows astronomers to study the formation of the first galaxies, analyze exoplanet atmospheres, and probe cold regions of space that are invisible to optical instruments. Operating space telescopes presents unique challenges, including thermal management, radiation protection, and the inability to perform repairs or upgrades, with few exceptions like Hubble. Despite these challenges, their contributions to science have been transformative. Fact 4. Robotic probes have visited every major planet in our solar system. Robotic space probes have become essential tools for exploring the solar system. Unlike crewed missions, these probes can travel to distant planets, moons, and other celestial bodies without the need for life support systems. They carry scientific instruments designed to study surface composition, atmospheric properties, magnetic fields, and internal structures. Beginning with Mariner 2's successful flyby of Venus in 1962, robotic probes have since visited all 8 major planets. The Voyager 1 and Voyager 2 missions, launched in 1977, conducted the first grand tour of the outer planets, Jupiter, Saturn, Uranus, and Neptune. These missions provided the first close-up images of many planetary systems and discovered new moons and rings. Closer to Earth, probes such as Mars Reconnaissance Orbiter, Curiosity rover, and Perseverance rover have studied the Martian surface in great detail. These missions have analyzed soil samples, searched for signs of past water activity, and tested technologies for future human exploration. Venus has been visited by multiple missions, including NASA's Magellan and the Soviet Venera landers, which successfully transmitted data from the surface. Jupiter and Saturn have been studied extensively by spacecraft such as Galileo and Cassini, both of which entered orbit around their target planets and delivered long-duration observations. Cassini also deployed the Huygens lander, which touched down on Saturn's moon Titan, capturing the first images from the surface of a moon with a dense atmosphere. Meanwhile, the New Horizons mission completed the first flyby of Pluto in 2015, revealing a complex and geologically active world. These missions have greatly expanded our understanding of planetary systems, leading to new models of planet formation and evolution. They have also provided critical data for planning future exploration, including sample return missions and the search for life. Fact 5. International space stations allow long-term research in microgravity. The development of orbital space stations has enabled continuous human presence in space and opened new avenues for long-term scientific research. The most prominent of these is the International Space Station, ISS, a collaborative project involving space agencies from the United States, Russia, Europe, Japan, and Canada. Launched in stages beginning in 1998, the ISS orbits Earth at an altitude of roughly 400 kilometers and travels at a speed of about 28,000 kilometers per hour. It serves as a microgravity laboratory where astronauts conduct experiments in a wide range of disciplines, including biology, physics, medicine, and materials science. Research on the ISS has led to important discoveries about how the human body responds to extended periods in space. Scientists have studied bone loss, muscle atrophy, changes in the cardiovascular system, and the effects of radiation exposure. This knowledge is critical for preparing future missions to the Moon, Mars, and beyond. The station also supports experiments in fluid dynamics, combustion, and crystallization that behave differently in microgravity than on Earth. For example, protein crystal growth experiments have improved our understanding of molecular structures, aiding drug development. The unique environment allows scientists to isolate physical processes without the interference of gravity. The ISS also serves as a platform for testing new technologies such as water recycling systems, autonomous robotics, and closed-loop life support, essential systems for deep space missions. It acts as a proving ground for hardware that will be used in more distant human exploration. The presence of international partners on the ISS has fostered cooperation and resource sharing in the global space community. Future space station initiatives, such as the planned Lunar Gateway, will build on this legacy to support missions beyond low Earth orbit. Fact 6. Reusable rockets are lowering the cost of accessing space. One of the most significant advancements in modern aerospace engineering has been the development of reusable launch systems. Traditionally, rockets used to access space were single-use. Their stages would fall into the ocean or burn up in the atmosphere after deployment. This approach meant that each launch required an entirely new rocket, which significantly increased cost and limited the frequency of missions. The introduction of reusable rocket stages has transformed spaceflight economics. By recovering and refurbishing parts of a launch vehicle, particularly the first stage, which contains the engines and fuel tanks, companies can dramatically reduce the cost per launch. The success of reusable rockets has led to an increase in the cadence of missions and made space more accessible for commercial, governmental, and scientific applications. The leading example of this technology is SpaceX's Falcon 9 rocket. Its first stage is designed to return to Earth either on a drone ship at sea or at a landing pad near the launch site. After landing, the stage can be inspected, reconditioned, and launched again. Some boosters have now been reused more than 10 times, demonstrating the durability and economic potential of the design. Reusable technology also enables the possibility of rapid turnaround, where launch vehicles are reused on short timelines without the need for extensive rebuilds. In addition to Falcon 9, vehicles like the Falcon Heavy and the upcoming Starship system aim to push reusability even further by applying it to both low Earth orbit launches and long-distance missions. Beyond SpaceX, other companies and agencies are also investing in reusable launch vehicles. Blue Origin's New Shepard and New Glenn rockets, Rocket Lab's Neutron vehicle, and Europe's upcoming reusable demonstrators are part of a growing global shift toward cost-effective space transportation. The implications are broad. Satellite constellations can be deployed more efficiently, science missions can fly more frequently, and the foundation is being laid for economically sustainable human spaceflight beyond Earth orbit. Fact 7. Mars rovers have driven across the red planet, studying its surface. Robotic exploration of Mars has advanced considerably over the past several decades, with multiple rovers sent to explore the planet's geology, climate, and potential for past life. These rovers are equipped with mobility systems that allow them to traverse varied terrain, as well as scientific payloads designed for in-situ analysis. The first successful rover on Mars was NASA's Sojourner, part of the Pathfinder mission in 1997. It demonstrated that small, mobile robots could operate autonomously on another planet. Sojourner traveled only a few meters, but it provided valuable data about Martian rocks and surface material. The next generation of rovers, Spirit and Opportunity, arrived in 2004. They were designed for 90-day missions but greatly exceeded expectations, with Opportunity operating for nearly 15 years. These twin rovers studied sedimentary rocks, dust devils, and mineral deposits, helping confirm that liquid water once existed on Mars's surface. Curiosity, which landed in 2012, is a car-sized rover equipped with a full laboratory suite. It has explored Gale Crater and climbed Mount Sharp, examining rock layers that provide insight into the planet's environmental history. Instruments like the Sample Analysis at Mars SAM unit allow Curiosity to detect organic molecules and gases such as methane. The most recent addition is Perseverance, which landed in early 2021 in Jezero Crater, an ancient river delta. It carries advanced instruments to search for biosignatures and collect rock cores for eventual return to Earth. Perseverance is accompanied by Ingenuity, the first helicopter ever flown on another planet. This aerial scout has helped guide the rover's path and proven that flight in the thin Martian atmosphere is possible. Rovers provide high-resolution imagery, detailed mineralogical data, and weather observations. Their long-duration presence on the surface allows them to operate across Martian seasons, offering comprehensive data that orbiters cannot supply. Future missions may include even more capable robotic explorers and the infrastructure needed for supporting human exploration. Fact 8. Satellites help with weather forecasting, GPS, and communication. Artificial satellites serve a wide range of practical applications that support daily life on Earth. Orbiting above the atmosphere, these spacecraft provide critical data for meteorology, navigation, global communications, and Earth observation. Weather satellites are positioned in both low Earth orbit and geostationary orbit to monitor atmospheric conditions across the globe. Instruments on board can detect cloud cover, storm formation, humidity levels, and surface temperatures. These datasets are used to model weather systems and provide early warnings for severe events like hurricanes, floods, and wildfires. Examples include NOAA's GO satellites and the European Meteosat series. Global Positioning System, GPS. Satellites operate in medium Earth orbit and transmit precise timing signals. A GPS receiver determines its position by calculating the time delay from multiple satellite signals. This system supports everything from smartphone navigation and autonomous vehicles to air traffic control and scientific research requiring accurate geolocation. Communication satellites, often in geostationary orbit, facilitate data transmission across continents. They carry transponders that relay television broadcasts, telephone calls, internet traffic, and secure military communications. Their ability to provide coverage to remote or underdeveloped regions is a key advantage over terrestrial networks. Earth observation satellites collect images and measurements of the planet's surface, oceans, and atmosphere. These data are used for agriculture, urban planning, environmental monitoring, and disaster response. Programs like Landsat and Sentinel have built decades-long archives of Earth imagery that support longitudinal studies of land use and climate trends. Satellite operations involve coordination across ground stations, onboard power systems, and propulsion mechanisms for maintaining proper orbit. Advances in miniaturization have led to the rise of small satellite constellations, enabling faster revisit times and lower costs per unit. As satellite deployment becomes more efficient, their impact on science, industry, and society continues to grow. Fact 9. Space missions have studied asteroids and even returned samples. Asteroids are remnants from the early solar system and provide clues about the materials and conditions that existed during planetary formation. Studying these objects helps scientists understand the origins of Earth and other terrestrial planets. Over the past 2 decades, several robotic missions have explored asteroids directly, some even returning samples to Earth. One of the first detailed studies came from NASA's Near-Shoemaker mission, which orbited and eventually landed on asteroid Eros in 2001. It provided close-up images and data on the asteroid's composition, structure, and surface features. This was followed by Japan's Hayabusa mission, which visited the near-Earth asteroid Itokawa and returned tiny samples to Earth in 2010. NASA's OSIRIS-REx mission, launched in 2016, traveled to asteroid Bennu, a carbon-rich body that may contain organic molecules and water-bearing minerals. After orbiting Bennu for nearly 2 years, the spacecraft performed a touch-and-go maneuver to collect a sample. The capsule carrying the sample was successfully returned to Earth in 2023, providing the most substantial extraterrestrial material collected since the Apollo missions. Japan's Hayabusa 2 mission similarly collected samples from the asteroid Ryugu, a dark rubble pile asteroid with a unique surface structure. The spacecraft delivered its sample capsule to Earth in 2020. These missions involved complex maneuvers, precision navigation, and autonomous guidance systems to operate in the low-gravity environments of small bodies. Other missions like NASA's DART, which impacted asteroid Dimorphos in 2022, are aimed at planetary defense research. By altering an asteroid's trajectory, DART demonstrated the potential to deflect future hazardous objects away from Earth. Continued asteroid exploration is expected to support scientific discovery, resource prospecting, and planetary defense strategies. Upcoming missions may include additional sample returns, in-situ resource utilization demonstrations, and even robotic mining concepts. Fact 10. Private companies are playing a major role in modern spaceflight. The space industry has seen a major shift with the increasing involvement of private companies. Historically, spaceflight was dominated by government space agencies, but today, commercial enterprises are launching rockets, building satellites, operating space stations, and planning interplanetary missions. This new model of public-private partnership has reshaped both the economics and accessibility of space. Companies like SpaceX, Blue Origin, and Rocket Lab have developed their own launch vehicles and infrastructure. SpaceX, in particular, has become a leader in orbital missions, satellite deployment, and human spaceflight through its Falcon 9 rocket and Crew Dragon spacecraft. It now routinely carries astronauts to the International Space Station as part of NASA's Commercial Crew program. Private companies have also deployed large satellite constellations to provide global internet access. SpaceX's Starlink network includes thousands of satellites in low Earth orbit, with more being added regularly. Other companies, such as OneWeb and Amazon's Project Kuiper, aim to create similar broadband networks. Blue Origin, founded by Jeff Bezos, is developing reusable launch systems with the goal of enabling space tourism and long-term human presence in space. Its New Shepard suborbital vehicle has completed multiple crewed flights, and its larger New Glenn rocket is under development for orbital launches. In the small satellite market, Rocket Lab has carved out a niche with its Electron rocket, optimized for frequent low-cost missions. Other companies are focused on satellite servicing, space debris removal, in-space manufacturing, and lunar logistics. Regulatory frameworks are evolving to keep pace with this expansion, and space agencies now routinely contract with private firms for services ranging from Earth observation to deep space missions. The collaboration allows agencies to focus on high-risk, science-driven projects while leveraging commercial innovation and cost efficiency. Private spaceflight has lowered barriers to entry, encouraged competition, and expanded the scope of what is possible in orbital and deep space operations. This shift is widely seen as a new chapter in human activity beyond Earth. Chapter 10: Fundamental Forces and Cosmological Theories. Fact 1. The universe is governed by 4 fundamental forces. All physical interactions in the universe can be traced back to 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces operate over different length scales, have distinct strengths, and govern the behavior of all matter and energy in the cosmos. Gravity is the weakest of the 4 forces, yet it is the most influential on large-scale structures such as planets, stars, galaxies, and the universe itself. It is always attractive and acts between any objects with mass. General relativity, developed by Albert Einstein, provides the modern description of gravity, framing it as the curvature of space-time caused by mass and energy. Electromagnetism is the force responsible for electricity, magnetism, and light. It acts between charged particles and is far stronger than gravity at the atomic and molecular scale. Electromagnetic interactions govern atomic structure, chemical bonding, and the behavior of charged particles in electric and magnetic fields. Unlike gravity, electromagnetism can be both attractive and repulsive, depending on the sign of the interacting charges. The strong nuclear force binds protons and neutrons together in atomic nuclei. It is the strongest of the 4 forces, but operates over extremely short distances, only within the range of a few femtometers. The force is mediated by particles called gluons, which act between quarks, the building blocks of protons and neutrons. Without the strong force, atomic nuclei would disintegrate due to the repulsive electromagnetic force between positively charged protons. The weak nuclear force is responsible for certain types of radioactive decay, such as beta decay, and plays a critical role in nuclear fusion in stars. It operates at short range and is mediated by the W and Z bosons. The weak force also contributes to the transformation of one type of quark into another and is integral to the process that fuels stars and produces elements in stellar cores. These 4 forces are described within the framework of quantum field theory, with 3 of them: electromagnetism, strong, and weak, successfully incorporated into the standard model of particle physics. Gravity, however, remains outside this model, and its reconciliation with quantum mechanics remains one of the major goals of modern theoretical physics. Fact 2. Gravity is not just a force, it bends space and time. Gravity, as described by general relativity, is fundamentally different from the other 3 forces. Rather than being transmitted by particles across space, gravity manifests as the curvature of space-time itself. In this framework, massive objects like stars and planets distort the fabric of space-time, and other objects move along curved paths in response. This concept replaces the classical Newtonian view of gravity, where a force acts at a distance between 2 masses. Instead, objects follow what are known as geodesics, paths of least resistance, through curved space-time. The stronger the gravitational field, the more space-time is curved, and the more these paths deviate from straight lines. One of the key predictions of general relativity is gravitational time dilation. Time runs more slowly in stronger gravitational fields. This has been confirmed experimentally by placing highly accurate atomic clocks at different altitudes and comparing their timekeeping. Clocks closer to Earth's surface tick more slowly than those at higher elevations, in agreement with the theory. Another important consequence is gravitational lensing. When light from a distant source passes near a massive object like a galaxy or black hole, the path of the light is bent, creating distorted or multiple images. This effect has been observed numerous times and is used by astronomers to map the distribution of dark matter and detect distant galaxies. The existence of gravitational waves, ripples in space-time caused by accelerating masses, was also predicted by general relativity. These waves were first directly detected in 2015 by the LIGO Observatory, confirming Einstein's theory a century after it was proposed. Events like black hole mergers and neutron star collisions produce these waves, which travel across the universe and carry information about their origins. General relativity remains the most accurate description of gravity to date and continues to pass every observational and experimental test. However, it is incompatible with quantum mechanics, and finding a unified framework that includes both remains a central challenge in physics. Fact 3. The Big Bang Theory explains the expansion of the universe from a hot, dense state. The Big Bang Theory is the leading scientific explanation for the origin and evolution of the universe. It states that the universe began from an extremely hot and dense state approximately 13.8 billion years ago and has been expanding ever since. This expansion continues today, with galaxies moving away from each other as space itself stretches. One of the key pieces of evidence for the Big Bang is the observed redshift of light from distant galaxies. Edwin Hubble discovered in the 1920s that galaxies are moving away from Earth, and the farther away they are, the faster they appear to recede. This relationship, known as Hubble's law, suggests that the universe is expanding uniformly in all directions. Another major confirmation came with the discovery of the cosmic microwave background radiation in 1965. This faint glow of microwave radiation, detected in all directions, is the cooled remnant of the early universe when it became transparent to radiation. It provides a snapshot of the universe approximately 380,000 years after the Big Bang, when atoms first formed and photons could travel freely. The Big Bang model also accurately predicts the abundance of light elements such as hydrogen, helium, and lithium. These elements were formed during the first few minutes of the universe's existence through a process known as primordial nucleosynthesis. The observed ratios of these elements closely match the theoretical predictions. In the first fraction of a second, the universe is thought to have undergone a period of rapid exponential expansion known as inflation. This phase smoothed out density variations and explains the uniformity of the cosmic microwave background, while allowing for the formation of large-scale structure through quantum fluctuations. The Big Bang Theory does not describe the actual bang or the conditions at the singularity where current physics breaks down. However, it provides a comprehensive framework for understanding the evolution of the cosmos from a hot, dense beginning to the complex structure observed today. Fact 4. The Standard Model explains how particles and forces interact. The Standard Model of particle physics is the theoretical framework that describes the fundamental particles of matter and the forces through which they interact, excluding gravity. It is one of the most successful and well-tested theories in all of science. According to the Standard Model, all matter is composed of two families of elementary particles, quarks and leptons. There are 6 types of quarks: up, down, charm, strange, top, and bottom, and 6 types of leptons, including the electron, the muon, the tau, and their associated neutrinos. These particles are grouped into 3 generations, with increasing mass and decreasing stability. Quarks combine in groups of 3 to form protons and neutrons, the building blocks of atomic nuclei. Leptons, such as electrons, orbit nuclei and participate in chemical reactions. Neutrinos, which have very little mass and no electric charge, rarely interact with other matter, making them difficult to detect. The forces in the Standard Model are mediated by particles known as gauge bosons. The photon carries the electromagnetic force, the W and Z bosons mediate the weak force, and gluons are responsible for the strong force. Each of these particles interacts with matter in specific ways and follows the rules of quantum field theory. A key feature of the Standard Model is the Higgs field, which gives particles mass through their interactions with it. The associated Higgs boson was discovered in 2012 at the Large Hadron Collider, confirming the last missing piece of the theory. Its discovery validated decades of theoretical predictions and opened new avenues for exploring physics beyond the Standard Model. Despite its successes, the Standard Model is incomplete. It does not include gravity, cannot explain dark matter or dark energy, and offers no explanation for the masses of neutrinos. Nevertheless, it remains the best current description of particle interactions and continues to guide research at particle accelerators and detectors worldwide. Fact 5. Unifying gravity with quantum mechanics is one of science's biggest challenges. While general relativity and quantum mechanics are individually successful in their respective domains, combining the two into a single, consistent theory of quantum gravity remains an unresolved problem. General relativity describes gravity as a smooth, continuous field affecting the curvature of spacetime, while quantum mechanics deals with discrete particles and probabilistic behavior. At large scales, general relativity accurately predicts the motion of planets, the dynamics of galaxies, and the behavior of black holes. At small scales, quantum mechanics governs the behavior of atoms, electrons, and subatomic particles. However, when these regimes overlap, such as near the singularity inside a black hole or at the beginning of the universe, both theories must apply, and their incompatibility becomes apparent. Several theoretical approaches have been proposed to bridge this gap. One of the most studied is string theory, which replaces point-like particles with one-dimensional strings. These strings vibrate at different frequencies, giving rise to the observed particles. String theory naturally incorporates gravity by predicting the existence of a graviton, the hypothetical quantum particle that mediates the gravitational force. Another candidate is loop quantum gravity, which attempts to quantize spacetime itself by describing it as a network of discrete loops. In this model, space is not continuous, but made up of finite units. Loop quantum gravity has had some success in describing the early universe and black hole entropy, but it is still a developing framework. Attempts to detect quantum gravitational effects are ongoing, but such experiments are challenging due to the extremely weak nature of gravity at quantum scales. Researchers are investigating possible signatures in cosmic microwave background patterns, gravitational waves, and high-energy particle interactions. A successful theory of quantum gravity would unify all four fundamental forces and provide a complete picture of the universe's fundamental workings. It would also offer new insights into black hole information, spacetime singularities, and the behavior of the universe at the smallest possible scales. Fact 6. Dark energy causes the accelerated expansion of the universe. Observations over the past few decades have revealed that not only is the universe expanding, but the rate of expansion is increasing. This surprising discovery implies the existence of a repulsive force or energy component that counteracts gravitational attraction on cosmic scales. This phenomenon is attributed to dark energy. Dark energy is a term used to describe the unknown cause of the universe's accelerating expansion. It is estimated to constitute approximately 70% of the total energy content of the universe. Unlike matter and radiation, dark energy does not clump together or dilute in the same way as the universe expands. Instead, its energy density appears to remain nearly constant or decrease very slowly over time. The first direct evidence for dark energy came from measurements of distant Type 1a supernova in the late 1990s. These exploding stars serve as standard candles, objects of known intrinsic brightness, allowing astronomers to determine their distances and recession velocities. The observations showed that the supernovae were dimmer than expected, indicating that the universe's expansion was accelerating. In addition to supernovae, evidence for dark energy comes from measurements of the cosmic microwave background, large-scale structure formation, and baryon acoustic oscillations. These independent observations converge on a cosmological model that includes dark energy as a dominant component. One common model treats dark energy as a cosmological constant, a term introduced by Einstein in his equations of general relativity. This constant represents a fixed energy density filling space uniformly. Another possibility is that dark energy evolves over time and may be described by a dynamic field, often referred to as quintessence. Despite being a central part of modern cosmology, the physical origin of dark energy remains unknown. It presents one of the greatest theoretical challenges in physics and has significant implications for the ultimate fate of the universe, whether it continues expanding forever, tears itself apart, or undergoes a phase change into a new state. Fact 7. Cosmic inflation explains why the universe is so uniform. Cosmic inflation is a theoretical framework that addresses several puzzling aspects of the early universe. It proposes that, in the first fraction of a second after the Big Bang, the universe underwent an extremely rapid exponential expansion. This inflationary phase smoothed out irregularities, stretched space, and set the initial conditions for the observable universe. One of the main problems inflation solves is the horizon problem. The cosmic microwave background radiation is remarkably uniform in temperature across the sky, even in regions that should not have been in causal contact. Inflation explains this uniformity by postulating that all regions were once close together before being stretched beyond each other's horizons. Another issue resolved by inflation is the flatness problem. The geometry of the universe appears to be very close to flat, meaning the total energy density is near the critical value needed to halt expansion without causing recollapse. Inflation drives the universe toward flatness, similar to how the surface of a balloon appears flatter as it inflates. Inflation also explains the absence of exotic relics like magnetic monopoles, which are predicted by some high-energy theories but have not been observed. By expanding the universe so rapidly, inflation would dilute these relics to undetectable levels. Importantly, inflation predicts the generation of tiny quantum fluctuations that were stretched to macroscopic scales. These fluctuations became the seeds for all structure in the universe: galaxies, clusters, and cosmic voids. Their imprint is visible in the cosmic microwave background as slight temperature variations, measured with high precision by instruments such as the Planck satellite. While inflation is widely accepted as part of the standard cosmological model, its underlying mechanism remains speculative. Various models propose different scalar fields and potential energy functions to drive inflation. Future experiments may help distinguish between these models by measuring the polarization and spectrum of cosmic microwave background fluctuations or searching for primordial gravitational waves. Fact 8. Neutrinos are nearly massless particles that rarely interact with matter. Neutrinos are elementary particles belonging to the lepton family. They are electrically neutral and interact only via the weak nuclear force and gravity, making them incredibly difficult to detect. Neutrinos are among the most abundant particles in the universe, yet they can pass through entire planets without interacting. There are three known flavors of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. These flavors correspond to the charged leptons with which they are associated. Neutrinos are produced in a variety of natural processes, including nuclear reactions in the Sun, radioactive decay, supernova explosions, and interactions in Earth's atmosphere caused by cosmic rays. For many years, neutrinos were thought to be massless. However, the discovery of neutrino oscillations, where one type of neutrino transforms into another, revealed that they must have mass, though extremely small. This discovery was awarded the Nobel Prize in Physics in 2015 and requires physics beyond the standard model, which does not accommodate neutrino mass. Neutrino oscillations have been observed in experiments such as Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada. These observations have provided measurements of the differences in mass between neutrino types, but the absolute masses are still unknown. Determining the mass hierarchy, whether one type is significantly heavier than the others, is an ongoing goal of current research. Detecting neutrinos requires specialized instruments with large volumes of material. For example, detectors often use vast tanks of water or heavy elements placed deep underground to shield them from background radiation. When a neutrino interacts with a nucleus in the detector, it produces a flash of light or a secondary particle that can be observed. In addition to their role in particle physics, neutrinos have astrophysical importance. They provide information about the core of the Sun, the mechanism of supernova, and the conditions in the early universe. Neutrino astronomy is a growing field, with observatories like IceCube at the South Pole detecting high-energy neutrinos from distant cosmic sources. Fact 9. Gravitational waves carry information about collisions in space. Gravitational waves are ripples in the fabric of space-time caused by the acceleration of massive objects. Predicted by Einstein's general theory of relativity in 1916, they remained undetected for nearly a century due to their extremely weak effects. These waves propagate at the speed of light and carry energy away from systems undergoing dynamic gravitational changes. The first direct detection of gravitational waves occurred in 2015 when the Laser Interferometer Gravitational Wave Observatory, LIGO, observed the merger of two black holes over 1 billion light-years away. The event produced a signal lasting a fraction of a second, which was recorded as a change in the length of the detector's arms by less than the width of a proton. Gravitational waves are generated by events involving massive, compact objects such as black hole mergers, neutron-star collisions, and possibly even asymmetric supernovae. These waves stretch and compress space-time as they pass, affecting the distance between objects in a measurable but extremely small way. Detectors like LIGO and Virgo use laser interferometry to measure these minute changes. 2 or more arms, each several kilometers long, are used to detect variations in length caused by passing waves. The detectors must be isolated from seismic noise, thermal fluctuations, and other environmental factors. The detection of gravitational waves has opened a new observational window into the universe. Unlike electromagnetic radiation, which can be absorbed or scattered, gravitational waves travel virtually unimpeded through matter. This allows astronomers to observe regions that would otherwise be hidden, such as the interior of merging black holes. In 2017, gravitational waves were observed from a binary neutron-star merger. This event was also detected across the electromagnetic spectrum, marking the beginning of multi-messenger astronomy. It provided insights into the origin of heavy elements like gold and platinum, and confirmed that such mergers can produce short gamma-ray bursts. Future observatories, including LISA, Laser Interferometer Space Antenna, will extend gravitational wave detection to lower frequencies, enabling the study of supermassive black hole mergers and potentially signals from the early universe. Fact 10. The fate of the universe depends on its density and the nature of dark energy. The ultimate fate of the universe is determined by its total energy density and the properties of dark energy. There are several theoretical scenarios for how the cosmos may evolve over time, each dependent on precise measurements of these fundamental quantities. If the universe contains enough matter and energy to halt its expansion, gravitational attraction could eventually reverse the expansion, leading to a big crunch. In this model, the universe would stop expanding and begin to contract, ending in a state of extremely high density and temperature, possibly similar to its beginning. If the energy density is exactly equal to the critical density and dark energy acts like a cosmological constant, the universe will continue to expand forever, but at a decreasing rate, approaching a steady state. In this case, galaxies will gradually move apart and star formation will decline as fuel is consumed, leading to a cold, dark universe. In the currently favored model, known as the lambda cold dark matter, LCDM model, the universe is flat and dark energy has a constant density. This leads to an accelerating expansion. Over trillions of years, galaxies will recede beyond observable distances, and only local structures bound by gravity will remain visible. An alternative scenario, if dark energy increases over time, is the Big Rip. In this case, the expansion accelerates to the point where it overcomes all forms of binding force, galactic, atomic, and even subatomic. Eventually, all matter would be torn apart. This scenario requires specific behavior of dark energy, which is still uncertain. Understanding the future of the universe requires accurate measurements of the Hubble constant, the equation of state of dark energy, and the curvature of spacetime. Observations from supernova, baryon acoustic oscillations, and cosmic background radiation all contribute to refining these parameters. Cosmological modeling and observations continue to evolve, and while several possible outcomes remain viable, current evidence supports continued accelerated expansion driven by dark energy, leading to a gradually cooling and increasingly isolated universe. You've just traveled through 10 chapters and 100 quiet facts about our universe. If your mind is still gently awake and curious, there's another video waiting, ready to take you even farther. But if sleep has found you, then rest easy. The stars will still be here when you wake. Good night and sweet dreams among the stars.